Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the story of the Big Bang, the calm, breathtaking beginning of space, time, and light itself. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the dawn of everything, where nothing became something, and silence became the first sound of creation. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. The phrase Big Bang can sound dramatic, even violent, as if the universe started with a single deafening explosion that flung matter into empty space. But that image is a little misleading. The truth is softer, stranger, and far more beautiful. The Big Bang wasn't an explosion in space, it was an expansion of space itself. The stretching of the very fabric that holds everything. Imagine dots drawn on a balloon. As the balloon inflates, each dot moves away from every other, not because the dots are travelling across the surface, but because the surface itself is expanding. That's closer to how the universe grows. There is no centre from which everything bursts outward, and no edge where it ends. Only endless fabric, gently stretching. Wherever you are in this universe, it looks as though everything is moving away from you. If you stood on a galaxy 10 billion light years away, you would see the same pattern. Galaxies receding in every direction, the same steady hum of expansion. It's as if the cosmos allows every observer to feel at the centre of what they can see, not because there is a centre, but because space expands evenly everywhere. Our visible universe, the part we can detect, is just a bubble inside a much larger whole, limited not by walls or boundaries, but by the distance light has been able to travel since the beginning. That light, stretched and softened by time, still reaches us. It carries the record of how this expansion began and how it continues today. In the early 20th century, astronomers started noticing that the light from distant galaxies was slightly redder than expected. When light waves stretch, their colour shifts toward red, and the farther the galaxy, the greater the redshift. It was as if the fabric of space itself was pulling those waves longer as it expanded. This gentle stretching of starlight became our first clue that the universe wasn't static at all, it was growing. In 1929, Edwin Hubble published his famous observation: the speed at which a galaxy appears to move away is directly proportional to its distance. The farther the galaxy, the faster the retreat. It wasn't galaxies fleeing through emptiness. It was space itself expanding, carrying them apart. A Belgian priest and physicist, Georges Lemaitre, had predicted this pattern years earlier, describing a primeval atom, a universe once condensed into a single point, before it began to unfold. Between Hubble's redshift and Lemaitre's mathematics, the idea of a dynamic, expanding universe took hold. You might imagine this expansion as something rushing outward, but that too can be misleading. The galaxies aren't sailing through a cosmic ocean, the ocean itself is swelling. Even empty space has scale. Distances grow between all things, while each galaxy remains relatively still within its own small patch. The Milky Way isn't racing through space in the usual sense. Rather, the space between galaxies is stretching, like taffy slowly being pulled. Try to picture it in smaller terms. Imagine standing on a quiet shore, watching waves pull the tide gently outward. The sand beneath your feet doesn't move, but the water between you and the horizon stretches wider, slowly carrying tiny boats farther apart. That's what the universe is doing, everywhere, all at once. As the expansion continues, light travelling through space also stretches. This is why the light from the most distant galaxies appears not only redder, but older, a message written in long, fading wavelengths. When astronomers study those faint signals, they're not just seeing distant space, they're looking back in time. Every telescope is a time machine, catching photons that left their sources billions of years ago. When you gaze at a distant star, you're seeing it as it once was, not as it is now. The night sky is a living archive, its stars arranged not only across space, but across time itself. If we trace all those stretched waves backward, every galaxy, every photon, they converge to a time when the universe was much smaller, denser, and hotter. There was no empty background waiting to be filled. The background itself was the thing that grew. In those first fractions of a second, the entire cosmos was compressed into a sea of energy. Space and time intertwined so tightly that the laws of physics as we know them didn't yet exist. There was no before, because before requires time, and time was still being woven into existence. This is what we mean when we say the universe had a beginning. Not a moment when something appeared inside a void, but when the void itself began to exist, when distance, direction, and duration all emerged together. You might think of it less as a firework and more as a dawn, not a bang, but a brightening. And though we can describe it, with equations and telescopes, the truth remains quietly poetic. Somewhere in that first instant, expansion began, and it never stopped. The same process that pushed galaxies apart billions of years ago is still happening around you now, in every cubic centimetre of space between atoms, between stars, between thoughts. So when you take a slow breath tonight, remember, the air you inhale has been stretched by cosmic history. The distance between particles in your lungs is larger now than it was a moment ago, not enough to feel, but enough to remind us. Everything is still unfolding. The universe didn't explode and end. It expanded, and it still is. If you listen closely, in the hush of that idea, there's something comforting. A reminder that expansion isn't chaos. It's motion with direction, growth with quiet purpose. From that first moment to this one, the cosmos continues to breathe, softly, patiently, forever becoming a little larger, a little older, and a little more full of light. In the last part of our quiet journey, we imagine the universe not as an explosion, but as a slow, steady expansion, space itself stretching like breath drawn into a sleeping lung. But how do we know that this isn't just a beautiful story? How do we know that space truly expands? That the galaxies are not sailing through some invisible sea, but being carried outward by the sea itself? The answer lies in light, the universe's oldest messenger, the one thread connecting us to everything that has ever shone. Let's drift back to the 1920s, to a time when our galaxy was thought to be the entire universe. Telescopes were smaller, the sky was simpler, and most astronomers believed the cosmos was static and eternal. Then came Edwin Hubble, working at Mount Wilson Observatory, peering through the crisp California night with a telescope that, at the time, was the most powerful eye humanity had ever built. He was measuring the faint glow of distant spiral nebulae, objects whose nature was still a mystery. Were they clouds inside our own galaxy, or something far beyond? Hubble's careful observations revealed something astonishing. Those nebulae were not part of the Milky Way. They were other galaxies. Whole islands of stars, each vast and separate, floating far outside our own. But there was more. When he looked at their light through a spectroscope, the delicate rainbows of their starlight seemed slightly shifted toward the red end of the spectrum. It was a subtle stretching, like a note of music played just a little lower than expected. This shift, known as redshift, was the universe whispering its motion. As light travels through space, if the space itself expands, its waves are stretched. Their crests drift farther apart, and when waves stretch, their colour slides toward red. If the galaxies were drawing near, we would see their light compressed and tinted blue. But what Hubble saw was the opposite, red upon red upon red. The farther away a galaxy was, the more its light was stretched. This pattern wasn't random. It followed a simple, haunting rhythm, distance and velocity rising together, as if every distant light were part of the same quiet exhale. When Hubble plotted the data, he found a nearly perfect line, a direct relationship. The farther a galaxy is, the faster it recedes. In other words, the more space lies between us, the faster that space expands. He published his results in 1929, a modest paper that quietly redefined our place in existence. The equation behind it was simple. Velocity equals a constant times distance, but the meaning was immense. It said the universe was not still, it was growing. That constant, later known as the Hubble constant, tells us how fast the cosmos expands even today. We measure it in kilometers per second per megaparsec, which means for every 3.3 million light-years of distance, the galaxies appear to recede by about 70 kilometers each second. You don't need to remember the numbers. Just imagine the space between distant galaxies stretching at the speed of a passing cloud, endlessly, effortlessly, without sound. Of course, Hubble didn't work alone. Years earlier, a Belgian priest and physicist named Georges Lemaitre had already proposed the idea of a universe that was expanding. He described it as a primeval atom, a cosmos born from something unimaginably compact that grew into the vastness we see now. His equations, drawn from Einstein's general relativity, predicted exactly what Hubble would later observe. The farther away a galaxy is, the faster it should appear to move. It was as if Lemaitre had heard the faint melody before anyone else, and Hubble had finally caught it echoing through the stars. To visualize this expansion, imagine a dark ballroom filled with lanterns. At first, all the lanterns are close together, their lights overlapping. Then, slowly, the room itself begins to stretch. The floor expands, the walls retreat. From any single lantern, all the others seem to drift away, their glow softening with distance. Yet none of them move through the air. The air itself is what grows. The farther the lantern, the dimmer its light, the deeper its hush. Even now, telescopes are listening to that cosmic hush. When astronomers measure the light of distant galaxies, they see the same pattern Hubble saw, only more precisely. Some galaxies show redshift so large that their light has been stretched by factors of 10 or more. Light that began as brilliant ultraviolet billions of years ago now reaches us as faint invisible radio waves. The light is tired, not because it's slowed down, but because the space it travelled through has stretched 1,000 times over. To measure this, astronomers use instruments so sensitive they can detect changes in colour, smaller than the tiniest whisper of a note. A galaxy's redshift tells us not only how far away it is, but how much the universe has expanded since its light began the journey. Each photon is a time capsule, its wavelength a record of distance and history. To look farther into space is to look deeper into time, not metaphorically, but literally. If you could stand outside the universe, which of course you can't, you would see not galaxies racing through emptiness, but space itself expanding, carrying them along like leaves on a widening river. The galaxies aren't fleeing from some central point. Every place expands, every distance grows. There is no centre, no edge, no boundary you could point to and say, it began here. Instead, the entire cosmic fabric swells together, everywhere, all at once. And what about the space between the stars, between atoms, between you and the air around you? On those small scales, gravity and molecular forces hold things together tightly enough to resist the expansion. The Milky Way stays whole. The Earth doesn't drift away from the Sun. Your atoms don't grow apart. The expansion of the universe is a gentle stretching, felt only across the deepest gulfs. It is the breathing of the cosmos on a scale so vast that we can only sense it through light itself. When Hubble's discovery first spread, not everyone believed it. Even Einstein resisted the idea of a dynamic universe. He preferred something eternal and steady. But when he saw Hubble's data, he reportedly called his earlier belief in a static cosmos the greatest blunder of my life. It was a rare moment when mathematics and observation met perfectly, revealing that even space and time are not fixed but alive, unfolding. All around us, that unfolding continues. Every second, the light from distant galaxies grows a little redder, a little older, a little quieter. The night sky you see now is not the same sky the Earth once knew, because the very distances between stars and clusters are changing. The universe itself is a song still playing, the longest, slowest symphony ever composed. And if galaxies are drifting apart in this cosmic rhythm, then the question naturally follows, what started the music? What first set the tempo of this endless expansion? Somewhere, buried in the oldest light, the universe still carries the memory of its first note, the faint afterglow of creation, humming softly through space, and it's to that whisper, that nearly invisible glow, that will turn next, the universe's baby picture, drawn in microwaves and still glowing all around you tonight. Imagine for a moment that the light we see in the night sky could speak. It would tell you stories from across billions of years, about the births of stars, the slow drifting of galaxies, and the earliest moments when space itself was still glowing. That light is all around us, even now. It doesn't just come from stars or galaxies, it fills the universe like a soft, invisible fog, the afterglow of creation itself. Astronomers call it the cosmic microwave background, or CMB, but you could think of it simply as the universe's baby picture, the faint warmth that never faded. The story of how we found it is, in a way, a happy accident. In 1965, two radio engineers named Arno Penzias and Robert Wilson were working at the Bell Telephone Laboratories in New Jersey. They were testing a large, gleaming antenna, a sort of giant metal ear designed to pick up faint signals from satellites. But no matter what they did, they kept hearing a persistent hiss of static. They checked everything, the electronics, the cables, even a pair of pigeons that had taken up residence inside the antenna and left an inconvenient layer of evidence behind. They cleaned, they recalibrated, they tried again. The noise was still there, a soft, steady hum coming from every direction, day and night. What they had stumbled upon, quite by chance, was the oldest light in the universe. Radiation released nearly 14 billion years ago, when the cosmos was just beginning to cool and become transparent. That faint hiss was not an error. It was history. It was the sound of light that had been travelling since the universe's childhood, finally reaching a pair of puzzled engineers on a quiet afternoon in New Jersey. To understand what that light represents, imagine the universe in its earliest days, hot, dense, glowing with energy. At that time, space was filled with a mixture of particles and light that couldn't escape. Photons, the particles of light, were constantly bouncing off electrons and protons trapped in a blinding fog. The universe was like the surface of the sun, opaque and brilliant. As space expanded, it cooled, until one day, about 380,000 years after the beginning, the temperature dropped low enough for electrons and protons to combine and form the first atoms. For the first time, the fog lifted. Light was free to travel. Those photons began their journey across the cosmos, spreading, stretching, and cooling with the expansion of space. Today, after nearly 14 billion years, we still see that same light, though it has shifted far into the microwave part of the spectrum. It has cooled to just 2.7 degrees above absolute zero, a whisper of warmth filling every corner of the sky. If your eyes could see microwaves instead of visible light, the night sky would look completely different. You wouldn't see points of starlight. You'd see an even, gentle glow covering everything, smooth and almost featureless. It would be like looking at the universe's baby photo, taken when it was only a few 100,000 years old. And just like a photograph, that light holds details. It's not perfectly uniform. It has tiny variations, small ripples in temperature, only a few millionths of a degree warmer or cooler than the average. Those faint ripples are among the most important discoveries in all of science. They are the fingerprints of the early universe, the seeds from which galaxies, stars, and eventually we ourselves would grow. Imagine the surface of a still pond disturbed by the smallest breeze. The ripples spread, overlap, and eventually form patterns. In much the same way, these early wrinkles in the cosmic microwave background became the scaffolding on which matter would gather under gravity's pull. Every galaxy we see today began as one of those subtle ripples in that ancient light. For decades, astronomers worked to capture and map those tiny variations. The first major step came in 1992 with a satellite called COBE, short for Cosmic Background Explorer. It measured the CMB with enough precision to confirm what theory had long predicted. The spectrum of this radiation matched that of a perfect black body, the signature of something that once glowed in thermal equilibrium. It was as if the universe itself had been a vast furnace that slowly cooled, leaving behind a flawless imprint of its temperature. Later missions like WMAP, the Wilkinson Microwave Anisotropy Probe, and Planck refined this map in exquisite detail. These satellites charted the tiny temperature differences across the sky, painting a picture of the infant universe with incredible precision. Every patch of slightly warmer or cooler light corresponded to regions where matter was a little denser or thinner, the earliest outlines of cosmic structure. When we look at those images, often coloured in blues and reds to represent slight temperature shifts, we're not seeing stars or galaxies, we're seeing the blueprint of everything that would come after. The red spots are places where the universe was just a little hotter, a little denser, destined to become clusters of galaxies. The blue areas were slightly cooler and would stretch into vast cosmic voids. It's like seeing the faint brushstrokes of a masterpiece long before the artist added any detail. The CMB also tells us the universe's age, shape, and contents. By measuring how those temperature ripples are distributed, their size, frequency, and amplitude, cosmologists can calculate the total amount of matter, the proportion of dark energy, and even the geometry of space itself. The results tell us something quietly profound. The universe is astonishingly flat. Not flat like a sheet of paper, but flat in its overall geometry, meaning that parallel lines stay parallel across cosmic distances. Inflation, that brief moment of rapid expansion in the first instant, ironed out any curve that might have existed, leaving space smooth and uniform. Every photon from the CMB has been travelling to us for almost 14 billion years. Along the way, the expansion of space stretched their wavelengths by a factor of about 1,000, turning once blazing light into gentle microwaves. These ancient photons reach Earth from every direction, arriving in equal measure, wrapping us in a subtle glow of cosmic memory. Sometimes, late at night, when astronomers turn their radio telescopes to the sky, they listen to that whisper. And if you've ever tuned an old television to an unused channel and seen the speckled snow of static, about 1% of that noise came from the cosmic microwave background, a remnant of the beginning flickering right there on your screen. It's strange and humbling to realise that no matter where you point an antenna, no matter where you are in the universe, this same faint hum greets you. It's the cosmos saying, "I remember. The light that began when atoms first formed has never stopped travelling." It has passed through clusters of galaxies, through the cold reaches between stars, through the air you breathe. You are, in a very literal way, bathed in the afterglow of creation. And as we study that glow, the temperature of 2.7 degrees above absolute zero, the delicate ripples no larger than 1 part in 100,000, we are seeing the first evidence that connects theory and observation in a single elegant truth. The universe began hot, dense, and full of light. That light still surrounds us. It is the oldest thing you will ever experience, the first story the cosmos ever told, still unfolding softly in every direction you look. If the cosmic microwave background is the baby picture of the universe, then what happened before that image was taken was its earliest heartbeat, the moment when the first ingredients of everything were forged. Long before there were stars, planets, or galaxies, the universe was a glowing sea of particles so hot and dense that nothing could hold together for long. But as it expanded, it began to cool, and for a few brief minutes, just the first 20 minutes or so after the beginning, the cosmos became a kind of cosmic kitchen. In that fleeting moment, almost all the ordinary matter that would ever exist was made. Physicists call this brief period Big Bang nucleosynthesis, but that phrase sounds colder than the event itself. It might be easier to imagine it this way. The universe was once a vast, radiant forge. At first, it was too hot for anything stable to exist. Temperatures of billions of degrees, where even protons and neutrons, the building blocks of atoms, were still finding their place. But as space stretched, the fire softened. The chaos began to settle. The energy that filled every inch of space started to condense into particles, and those particles began to link together in new and surprising ways. In the first second, protons and neutrons began to appear, tiny bundles of matter made of quarks, held together by the strong nuclear force. It was a time when matter and antimatter still danced closely, almost in balance. For every billion particles of matter, there were roughly a billion antiparticles that would annihilate in flashes of light, leaving behind a faint surplus of ordinary matter, just enough to build all the stars, planets, and living things that would ever exist. Without that tiny imbalance, everything would have vanished back into pure radiation, and there would be no you, no me, no anything at all. As the universe passed its first second, it was filled with light and a swirling mixture of particles, electrons, protons, neutrons, neutrinos, and photons, all colliding constantly, too energetic to stay bound together. But in just a few more seconds, as the temperature dropped below 1 trillion degrees, protons and neutrons could finally hold hands long enough to form the first atomic nuclei. The chemistry that followed was simple but profound. Most of the protons stayed single. They became hydrogen, the simplest and most abundant element in the universe. Some protons joined neutrons to form deuterium, a heavier version of hydrogen with 1 neutron attached. 2 deuterium nuclei could fuse to create helium, the second lightest element, and a few rare combinations produced traces of lithium and beryllium, though most of those quickly broke apart again. In those first minutes, the entire cosmos was performing fusion, not inside stars but everywhere at once. It was as if every cubic meter of space were a tiny star, burning not from gravity but from the sheer heat of creation. Then, as quickly as it began, the reaction faded. As the universe continued to expand, the temperature dropped below the level needed for fusion to continue. Within about 20 minutes, the cosmic forge had cooled too much to make anything new. The era of element making was over. When astronomers look around the universe today, they see the fingerprints of that early chemistry everywhere. Roughly 75% of the visible matter is hydrogen, about 25% is helium, and less than 1% consists of everything else: lithium, carbon, oxygen, nitrogen, and so on. The heavier elements came much later, inside stars that forged them in their fiery hearts. But the hydrogen and helium, the raw materials of stars themselves, were made in that first cosmic breath. We can even test this story with astonishing precision. When telescopes measure the light from ancient gas clouds and distant galaxies, the proportions of hydrogen and helium match exactly what the equations of nucleosynthesis predict. That harmony between theory and observation is one of the strongest confirmations we have that the Big Bang model is correct. It's as if the universe wrote its own recipe on the sky and invited us to check the ingredients. Still, there's one small mystery that remains unsolved: lithium. According to the calculations, there should be about 3 times more lithium than we actually observe in old stars. This discrepancy is known as the lithium problem. It's a tiny detail, but it's a reminder that even our most elegant models are still incomplete. Somewhere in those first minutes, something happened that we don't fully understand. Perhaps a subtle process in nuclear physics, or a clue about new particles we haven't yet discovered. The universe, like any good storyteller, keeps a few secrets to itself. As the first elements formed, the universe became a simpler, quieter place. The blinding radiation still filled it, but the energy was spreading out, softening with every moment. The newborn atoms were still ionized, stripped of their electrons, so light couldn't travel freely yet. Photons continued to scatter off charged particles, turning the whole universe into a thick, radiant fog. If you could somehow stand in that early cosmos, you wouldn't see anything in the ordinary sense. There would be no distinct shapes, no boundaries, just a glowing sea of light and matter, perfectly mixed. For about 380,000 years, that fog persisted. The universe kept expanding, the temperature falling from billions of degrees to just a few thousand. Finally, when it cooled enough for electrons to settle into orbits around nuclei, atoms could form and stay intact. That moment, when light and matter parted ways, is the one captured by the cosmic microwave background we talked about earlier. The glow we see today is the fossil light released when the universe became transparent. When you trace that light back to its origin, you're following a line that passes right through these early minutes, through the forge where hydrogen and helium were made. Every atom in your body owes its existence to that chemistry. The hydrogen in the water you drink was born then. The helium in birthday balloons, the fuel of every star, all of it came from that short, bright window at the dawn of time. It's extraordinary to think that the universe's first attempt at chemistry lasted less than half an hour, yet its results shaped everything that followed. In that tiny fraction of cosmic time, the universe built the foundation for galaxies, stars, planets, and life. The simplest elements became the alphabet of the cosmos, letters that would later form the complex sentences of stars and living cells. And when we look up at the night sky now, we're seeing the after effects of that first experiment in creation. Every shining star is simply hydrogen and helium trying, once again, to fuse and glow. The same process repeating in miniature. It's as though the universe never stopped writing its story in fire. It only slowed the tempo, letting us read it one heartbeat at a time. By now, we've wandered through the universe's first minutes, the era when atoms were forged and light began its long journey across space. But if we trace time backward even further, past the formation of hydrogen and helium, past the sea of glowing plasma, we reach a point where our understanding begins to fade. The light of knowledge dims there, and the universe hides behind what physicists call the Planck era, the first fraction of a second after the beginning, when everything we know about physics breaks down. This is the most mysterious region of cosmic history. It lasted less than what you could call 10 to the power of minus 43 seconds, a time so short that even imagination struggles to contain it. To say that the universe was small or hot doesn't quite capture it. In that instant, all of space, all of time, and all of the energy that would one day become galaxies and stars and thoughts was packed into a realm where gravity itself became quantum, flickering, uncertain, shifting from one possibility to another faster than any clock could ever tick. Physicists call this barrier the Planck curtain, not because there was an actual wall, but because it represents the edge of what our current theories can describe. Beyond it, the familiar rules, relativity for the large, quantum mechanics for the small, no longer fit together. It's as though we have built two beautifully precise maps, one for the mountains and one for the sea, but the coastline where they meet is drawn in fog. We can't quite see how the two landscapes connect. To cross that boundary, we would need a theory that unites gravity and quantum physics, something often called quantum gravity. String theory, loop quantum gravity and other ideas try to fill that gap, but for now, they remain works in progress. What we can do is listen to what the universe itself tells us through the patterns we can still observe today. The cosmic microwave background, the distribution of galaxies, even the presence of tiny ripples in space-time called gravitational waves, all of these may carry faint echoes of what happened before the curtain lifted. So what might it have been like, that first instant? No one can say for certain, but the best models suggest that the early universe was not calm or orderly. It was a storm of probabilities, a foam of energy where the geometry of space twisted and tangled in every possible way. Imagine watching the surface of boiling water, bubbles forming and collapsing faster than you can follow. That's the picture physicists use for space-time itself in that earliest moment, a quantum foam, restless and seething. In that chaos, even the idea of distance may not have existed. There was no where, no before, no after, in the usual sense. The universe didn't expand into space, because space itself hadn't yet taken shape. It wasn't born inside something, it was the birth of something itself. That's a concept the human mind can only circle around, never fully hold. But maybe you don't have to. Maybe it's enough to imagine the silence before the first note of music, the pause before a word is spoken, a stillness filled with potential. When we say time began, we don't mean a clock started ticking inside an empty void. We mean that the very idea of time, the flow from past to future, came into being along with everything else. Before that, asking what happened before the Big Bang may not make sense at all, because before is a word that requires time, and time had not yet been written into existence. Still, we can infer something about this hidden epoch by following the traces it left behind. For example, the universe today appears remarkably smooth and uniform. No matter where you look, the temperature of the cosmic microwave background is almost exactly the same, differing only by tiny fractions of a degree. How could that be, when distant regions of the sky were never close enough to exchange light or energy in the early days? That's one of the puzzles the Planck era leaves us with, a mystery known as the horizon problem. Another puzzle is the universe's shape. Observations show that on the largest scales, space is almost perfectly flat. A flat universe means that its total energy is balanced precisely between expansion and gravity's pull. A cosmic tightrope walk with no obvious reason it should be so stable. These clues suggest that something extraordinary must have happened just after the Planck curtain rose, something that smoothed and balanced the cosmos with astonishing precision. That something is what we now call inflation, a sudden brief burst of expansion that occurred in the tiniest fraction of a second after the beginning. It's as if the universe took a deep breath and grew unimaginably fast, stretching any irregularities into near-perfect uniformity. But we'll reach that part of the story soon. For now, let's linger a little longer at the edge of the unknown, at the place where the rules of reality blur into one another. If you could somehow watch the Planck era unfold, it might not look like anything we'd recognise. Space and time would be woven together so tightly that you couldn't tell one from the other. The concept of light would not yet exist, nor particles, nor even forces as we know them. Instead, there would only be energy, pure and undefined, curving in upon itself. It might not even make sense to call it energy. In the way we use the word, it was potential, waiting to express itself. Some scientists think that quantum fluctuations, tiny, random changes in that primordial field, could have triggered the birth of everything we see. In this picture, the universe wasn't created from nothing in the ordinary sense. It arose naturally from the laws of quantum physics, where uncertainty itself has creative power. A particle can flicker into existence for a moment, borrowing energy from the vacuum as long as it gives it back quickly enough. On the grandest scale, perhaps the entire universe is such a fluctuation, one that never collapsed, but instead kept growing, carried forward by its own expansion. You might picture that moment as a vast sea suddenly deciding to ripple. No outside hand pushed it. The ripple was simply allowed, an inevitable expression of what was possible. That's how modern cosmology often frames creation, not as an explosion, but as a spontaneous unfolding of the simplest possible laws. And though this might sound abstract, there's something comforting about it. It means the universe, for all its strangeness, is not an accident. It follows patterns, even when those patterns are too deep for us to fully understand. The Planck curtain hides the details, but behind it, the seeds of everything familiar, space, time, gravity, light, were already stirring. So we stand at the edge of knowledge, gazing into that first instant. The mathematics stops there, the experiments fall silent, but the imagination can still whisper what might have been. A flicker, a ripple, a breath that became everything. From that unknowable beginning, a sudden expansion will follow, a stretch so swift and profound that it will sculpt the very shape of the cosmos. The curtain will rise, and from behind it, inflation will begin. When the curtain of the Planck era lifted, the universe had no stars, no galaxies, not even atoms. It was a smooth ocean of energy, restless but without structure, waiting for something to give it shape. Then, in an instant so brief it defies imagination, everything changed. The calm sea became a rising tide. The universe expanded faster than anything ever would again. This brief, astonishing growth is known as cosmic inflation, the fastest stretch in history. It's hard to picture what vast means in this context. In less than 1/trillionth of a trillionth of a trillionth of a second, that is, about 10 to the power of minus 35 seconds, the universe grew from smaller than an atom to something larger than a galaxy. Space itself ballooned, carrying every point away from every other at speeds that dwarfed even light. Nothing moved faster than light, of course. The speed limit of nature remained intact. Instead, it was space that stretched, dragging everything within it outward, like dots on a rubber sheet that suddenly pulled in every direction. The idea of inflation began in the early 1980s, when a physicist named Alan Guth was trying to understand why the universe looked so astonishingly smooth. If we look at opposite sides of the sky, their temperatures are almost identical, differing by only 1 part in 100,000. But those regions were never close enough to share light or heat. How could they possibly have become so uniform? Inflation offered an answer. Before that rapid expansion, the universe was small enough for everything to mingle and reach thermal balance. Then, when inflation stretched it far beyond visible horizons, that evenness was carried outward, frozen into the fabric of space itself. Inflation also solved another puzzle, the universe's flatness. When we measure the geometry of the cosmos today, we find that it's neither curved inward like a sphere, nor outward like a saddle. On large scales, it's remarkably flat, meaning that parallel lines stay parallel even across billions of light years. That balance is delicate. Without inflation, the universe would have had to begin with a level of precision so improbable it seems almost impossible. Inflation stretched away any initial curvature, smoothing space like a sheet pulled tight. To imagine this, think of a small balloon that has wrinkles and folds when it's deflated. As you blow it up, those imperfections fade, the surface appearing smoother and flatter the larger it grows. Inflation did the same for the universe, ironing out its curves and wrinkles, leaving behind a cosmos that, on the grandest scales, is almost perfectly even. But inflation didn't just smooth the universe. It also planted the seeds of all future structure. During that rapid expansion, the quantum fluctuations, tiny random variations in energy that occur naturally in empty space, were stretched to cosmic size. What began as subatomic ripples became enormous waves in the density of matter and energy. When inflation ended and the universe slowed, those faint variations remained as imprints in the fabric of space. Over billions of years, gravity would amplify them into galaxies and clusters of galaxies, shaping the web of stars we see today. It's humbling to think that everything, from the swirl of a spiral galaxy to the pattern of light in the cosmic microwave background, traces back to quantum whispers during that first instant. The galaxies are, in a very literal sense, the frozen music of inflation. Random notes expanded until they became a cosmic symphony. After that explosive growth, inflation stopped as abruptly as it began. The energy driving it, what scientists call the inflaton field, decayed, releasing its stored power into a sea of particles and radiation. The universe reheated in a brief but intense flash, filling space with the ingredients of the Big Bang's next act: quarks, electrons, photons, and neutrinos. This transition from the inflationary vacuum to a hot, dense fireball is sometimes called reheating, but you can imagine it as the moment the stage lights came on. The dark potential energy transformed into the bright, tangible energy of matter and light. By the time this was over, the universe was only a fraction of a second old. Yet in that blink, its fate had been set. The geometry, the uniformity, the subtle irregularities that would form stars, all of it was decided during this unimaginable expansion. The universe was, in effect, written into its future by inflation's single breath. Even today, cosmologists search for evidence of this ancient event. The most promising clues are faint patterns in the polarization of the cosmic microwave background, a kind of cosmic fingerprint left by primordial gravitational waves, ripples in space-time itself created by inflation. Detecting those waves would confirm that space really did expand that fast, that early. Instruments like the BICEP array at the South Pole and the Planck satellite have hunted for these signals, and though the results are still uncertain, the search continues. The cosmos may be vast, but it still carries the memory of its first motion, encoded in light. The physics behind inflation is complex, but the idea itself is simple. Space has energy, even when it appears empty. Under certain conditions, that energy can act as a kind of pressure, pushing space to expand. If that pressure dominates for even a moment, it causes runaway growth, expansion feeding on itself until the energy dissipates. Inflation is that runaway moment, tamed by the cooling of time. There's something poetic in that balance. Too short and the universe would be chaotic and curved, full of tangled geometry. Too long, and it would have expanded so much that no galaxies could ever form. Somehow it lasted just long enough, a fraction of a heartbeat, to create a universe capable of structure, light, and life. When you imagine it, don't picture an explosion or a roar. Picture something gentler, a calm breath released after infinite stillness, a whisper that became a wind that became everything. Inflation wasn't violent, it was graceful, swift, and silent. The expansion itself made no sound because sound needs air, and there was no air, no space yet for it to move through. Only the smooth unfolding of existence, faster than comprehension, quieter than thought. And as that stretch ended, the energy condensed, light burst forth, and the universe began to glow. The next act was about to begin, matter taking shape from pure energy, particles forming, and the cosmos beginning to cool into something recognizable. The storm of creation would soften again, just enough to let atoms and light start their timeless dance. Somewhere in that still glowing haze lies the memory of inflation, a single, perfect balance between speed and silence. We can't see it directly, but every star, every galaxy, every breath we take is part of its legacy. It's the quiet proof that from a fraction of a second of extraordinary expansion came the infinite calm of the universe we know. When inflation ended, the universe was almost empty, not because there was nothing in it, but because the energy that filled space hadn't yet transformed into anything tangible. It was pure potential, smooth and silent, like a canvas waiting for paint. Then, in an instant, that potential began to spill over. The energy that had driven inflation decayed into a hot ocean of particles. In less than a fraction of a second, the universe filled with light and matter. The stage that had stretched so quickly now glowed with new creation. This transformation is called reheating, but that word feels too mechanical for what really happened. It was more like a storm of birth, the moment when the abstract became real. Imagine a single breath of wind turning into a hurricane. As the inflating field released its energy, the universe heated up to temperatures far beyond what any star could ever reach. In that incandescent sea, particles of every kind collided, appeared, vanished, and reappeared again. It was the first true dawn, though there was no sky yet to hold it. From that fire came the basic building blocks of everything that would ever exist. Quarks and antiquarks, tiny points that would later bind together to form protons and neutrons, flickered into being. Electrons and positrons, neutrinos and photons filled the space between them. For a while, matter and antimatter existed in near-perfect balance, creating each other and destroying each other in bursts of light. It was a dance of symmetry, as if the universe were painting with two identical brushes, one of matter, one of mirror matter, erasing as quickly as it created. But somehow, not everything cancelled out. For every billion particles of antimatter, there was one extra particle of matter left behind. That 1 in a billion imbalance is the reason anything solid exists today. The cause of it remains one of cosmology's great mysteries. Physicists call it baryogenesis, the process that tipped the scales in favour of matter. It required 3 delicate conditions: the breaking of certain symmetries in physics, interactions that treat matter and antimatter slightly differently, and a universe that was cooling fast enough for those differences to matter. We still don't know exactly how baryogenesis happened. It might have involved heavy, unstable particles decaying unevenly. It might have been triggered by neutrinos that interacted just enough to break the balance. Or it could have been something even stranger, a clue pointing toward physics beyond what we currently understand. But whatever caused it, that tiny preference for matter changed everything. It meant that as the universe continued to expand, a small residue of particles survived the mutual annihilation. Those survivors became the raw material for stars, planets, and life. Think about that for a moment. If the universe had been perfectly symmetrical, if matter and antimatter had existed in exactly equal numbers, every bit of mass would have been erased in a flash of radiation. There would be no galaxies, no atoms, no chemistry, no thought. The entire cosmos would be nothing more than a fading sea of light. All the richness of existence depends on that one small imperfection, a whisper of imbalance written into the laws of nature. As the universe cooled to temperatures of roughly 1 trillion degrees, quarks began to bind together. The strong nuclear force, the glue of the subatomic world, became powerful enough to trap them inside tiny clusters called hadrons. The simplest of these were protons and neutrons, familiar to us now but revolutionary then, the first stable building blocks. They moved through the dense, brilliant plasma like embers in a storm. Every cubic centimetre of space was alive with collisions. Photons bounced between particles billions of times each second. The universe was young, but already fiercely busy. Within the first microsecond, that's 1/1,000,000th of a second, the balance between matter and light shifted. Radiation still dominated, but matter had taken root. It wasn't evenly spread. There were tiny irregularities, the same quantum ripples stretched by inflation, and those variations meant that some regions were ever so slightly denser than others. Gravity began its quiet work, pulling those regions toward greater density, though the effect would take eons to show. Meanwhile, as temperatures dropped further, protons and neutrons started to join together through nuclear reactions. This marked the beginning of what we call Big Bang nucleosynthesis, which we explored earlier, the forging of hydrogen, helium, and traces of lithium. The groundwork for that process was laid right here, in these first fractions of a second, as the raw ingredients took shape. The physics of this time is extreme, but the story is almost tender. The universe was both violent and creative, collapsing and expanding, erasing and rewriting itself. Every flash of annihilation created new light. Every fleeting moment of imbalance built the foundation for something lasting. It's a reminder that creation and destruction aren't opposites, they're partners in a cosmic rhythm. Even today, we see echoes of that rhythm in particle accelerators on Earth. When physicists smash protons together at nearly the speed of light, they briefly recreate conditions similar to those first microseconds of the universe. Inside detectors miles underground, they search for the same fleeting traces, for signs of how matter once outlasted antimatter. Each collision is a miniature echo of that first great fire, a laboratory whisper of cosmic origin. As the universe continued to expand, the chaos gradually settled into order. Photons, the particles of light, began to dominate again, flooding space with radiation. Matter still existed, but in tiny quantities compared to the sea of light. Yet even then, the ratio was fixed, about 1 proton for every billion photons. That ratio has never changed. It's another silent fingerprint of those first moments, a balance that determined how the cosmos would evolve. By the time the universe was 1 second old, it had cooled to around 10 billion degrees, still unimaginably hot, but calm enough for neutrinos to slip free. These nearly invisible particles decoupled from matter, racing away at almost the speed of light. They've been travelling ever since, forming what we call the cosmic neutrino background, a relic even older than the microwave radiation we can detect. We can't see it, but it passes through you right now. Trillions of neutrinos from the birth of time, streaming silently through every atom in your body. The universe at this point was radiant, dense, and expanding fast. Its future, the formation of stars and galaxies, that was already written in its patterns of light and density. But for now, it was still young, glowing, and opaque. Space was filled with a plasma of particles and photons locked in constant interaction. Light could not yet travel freely. It would take hundreds of thousands of years before the cosmos cooled enough for that light to escape. The light we now see is the cosmic microwave background. From energy came matter, from symmetry came imperfection, and from imperfection came everything else. The laws of physics, quiet and precise, carried out their work without audience or applause, shaping a future they could never witness. And somewhere in that vast glow, the seeds of everything familiar, starlight, atoms, water, breath, waited for their turn to shine. The universe was no longer a place of pure energy. It had cooled enough for matter to exist, for protons and neutrons to form, and for the faint rhythm of order to begin. Yet it was still an ocean of light and particles so dense that nothing could travel far without colliding. The cosmos glowed from within, a radiant fog stretching in every direction. This was the age of plasma, a time when light and matter were inseparable, locked together in a bright, shimmering dance. If you could have stood there, though there was no solid ground to stand on, the scene would not have looked like anything familiar. Space itself would have been blazing white, but not from any single source. Every particle glowed, scattering light endlessly. You wouldn't have seen stars or colours or shadows, only brightness. The entire universe was one great lantern, still without form, but already filled with promise. At this time, roughly 1 second to a few minutes after the beginning, protons and neutrons were joining to create the first atomic nuclei. Hydrogen dominated, helium followed, and traces of deuterium and lithium flickered briefly into being. These reactions released enormous amounts of energy, adding to the brilliance of the plasma sea. The light wasn't free to escape yet. It was trapped, bouncing constantly between electrons and ions, like sunlight caught in a cloud. The density of matter was extraordinary. A single cubic meter of space, about the size of a large box, contained more mass than all the air in the atmosphere around Earth today. And yet, it was thinning fast. Every second, the universe doubled in size, stretching the distance between particles, cooling the fire by spreading it wider. The glow softened, turning from blinding white to a gentler amber as it expanded. This was a delicate balance between energy and gravity. Gravity, even in those early moments, was trying to pull matter together, to weave the first hints of structure. But radiation, the pressure of light itself, was pushing outward, keeping everything smooth and uniform. The two forces held each other in check, like two partners in a slow cosmic waltz. That balance would last for hundreds of thousands of years, setting the stage for all that came later. Inside that equilibrium, the smallest irregularities began to grow. Inflation had stretched tiny quantum ripples into subtle differences in density. One region just a little heavier, another just a little lighter. Those variations were unimaginably small, 1 part in 100,000. But gravity doesn't need much to begin its work. Over time, the denser patches would pull in more matter, while the thinner regions would become emptier. The great cosmic web, the pattern of galaxies that would one day fill space, had already begun to sketch itself invisibly beneath the surface of the plasma. But for now, the universe was still blind. Light could not travel freely. Each photon, each particle of light, survived only a fraction of a second before scattering off an electron and changing direction. It was as if every bit of light was trapped in an endless maze, its path twisted and turned billions of times before moving even a small distance. To imagine it, think of standing in a dense fog lit by 1,000 lanterns. The light is everywhere, yet you can't see the lanterns themselves. The photons in that early plasma were just as lost, unable to escape, constantly ricocheting between particles. The universe's first light existed, but it could not yet shine outward. Still, that light carried information. The temperature, the density, and the movement of the plasma left imprints in its energy. Those tiny variations trapped inside the fog would eventually emerge as the delicate ripples we now see in the cosmic microwave background, a perfect record of the universe's first glow. The photons remember everything. They were there when matter formed, when particles collided, when the universe took its first breaths of order. As time passed, the average temperature of the cosmos continued to fall. In the earliest moments, it had been billions of degrees, so hot that even atomic nuclei could not survive. But by the time a few minutes had passed, the universe had cooled to around 1 billion degrees. To us, that number is unthinkable, but to the cosmos, it was a sign of progress, a step toward transparency, toward light's eventual freedom. During this time, neutrinos had already slipped away, streaming across space almost without resistance. Unlike photons, neutrinos barely interact with matter, so they escaped early, becoming ghostly messengers from the universe's first second. Today, those same neutrinos are still passing through you by the trillions every second, almost entirely unnoticed. Silent travellers from the beginning of time. The young universe continued to cool and expand. The density dropped, collisions became less frequent, and the radiation grew dimmer and redder. The glow shifted slowly toward longer wavelengths as space stretched the light itself. Though it was still trapped, the photons were growing calmer, their energy softening as the cosmos breathed outward. This period lasted for a long time, hundreds of thousands of years. During all that time, the universe was a glowing plasma, hot, bright, and opaque. If you could somehow see it from outside, which of course you couldn't, because there was no outside, it would have looked like a perfect sphere of light expanding into darkness, its surface cooling and fading as it grew. Deep within that brightness, invisible scaffolds of dark matter were already shaping the future. Dark matter doesn't interact with light, so while photons bounced endlessly, dark matter could move freely, forming the first gravitational wells, gentle dips in the landscape of space where ordinary matter would eventually gather. It was like laying down the foundations of a city before anyone had drawn the streets. Those early dark matter halos would become the birthplaces of galaxies long after the light finally broke free. Eventually, after about 380,000 years, the temperature dropped to a few thousand degrees, cool enough for electrons to settle into stable orbits around nuclei. For the first time, atoms could form without being torn apart by collisions. When that happened, the fog of plasma cleared, and the light that had been trapped for so long was released. That moment of liberation created the glow we still see today as the cosmic microwave background, the universe's first visible sigh. But in this early plasma age, before transparency, the cosmos was more like a song hummed through water, muted, vibrating, and full of hidden rhythm. It was alive with motion, yet no sound could travel, because there was nothing solid to carry it. The only melody was the gentle push and pull between matter and light, a balance that defined everything to come. Every galaxy, every cluster, every atom in your body traces its history back to that luminous fog, to a time when light was both trapped and everywhere, when the universe was still deciding how to shine. In that radiant silence, the cosmos rehearsed its future, a world of light and shadow, of matter and emptiness, of endless expansion and delicate structure. It was, in every sense, the first act of the visible universe, a glowing promise waiting to be fulfilled. After hundreds of thousands of years of glowing fog, the universe was ready to breathe its first clear breath. The brightness that once filled everything had begun to fade. Space had stretched, the temperature had fallen, and for the first time since its beginning, the cosmos was calm enough for light to finally travel freely. It was the first clear morning, the dawn of transparency. At this moment, the universe was about 380,000 years old. Until then, it had been an ocean of plasma, hot, thick, and impenetrable, where light couldn't move, without being scattered at every turn. Photons, the particles of light, were constantly colliding with electrons, bouncing from one to the next in a chaotic dance. The universe wasn't dark, but it was blind. No light could cross any meaningful distance without being swallowed again by the storm. As the expansion continued, the fire of that early plasma began to cool. When the average temperature dropped to just under 3,000 degrees, cooler than the surface of the sun but still unimaginably hot by earthly standards, a delicate transformation took place. Electrons and protons, which had been flying separately through space, slowed down just enough to meet and stay together. They formed the first stable atoms, mostly hydrogen, with a trace of helium. For the first time, light and matter parted ways. Freed from the constant scattering, photons could now move through space without immediately colliding with anything. The fog lifted. The universe, for the first time in its history, became transparent. You might imagine it as the moment the sky of creation finally cleared after an endless storm. The blinding brightness softened into a golden glow. stretching across an infant cosmos hundreds of thousands of light years wide. The light released in that instant began to travel outward in all directions, carrying with it a perfect record of what the universe looked like at that moment. That light has never stopped travelling. Over the next 13.8 billion years, as space continued to expand, that ancient light stretched and cooled. Its colour shifted from glowing orange to invisible microwaves until it became the faint uniform radiation that surrounds us today, the cosmic microwave background, or CMB. It fills the sky in every direction, not as a beam or a flash, but as a soft, persistent whisper. It is the same light that escaped on that first clear morning, still arriving at our telescopes and our radios, older than any star, older than any galaxy. Every photon from that moment carries a story. Its wavelength, the distance between one wave crest and the next, has grown by a factor of more than 1,000 since it first set out. What began as fiery brilliance is now a gentle hum, with a temperature of just 2.7 degrees above absolute zero. You can think of it as the universe's memory, faded but not forgotten. Even now, a few of those ancient photons pass through you each second, silent travellers from a time before the first stars. If you could see that early scene, it would look nothing like the starry sky we know. There were no points of light, no galaxies or planets. Instead, everything glowed evenly, a smooth, endless horizon of warmth. In that glow were tiny ripples, subtle differences in temperature and density, like the faintest texture on the surface of calm water. Those ripples were the fingerprints of the future, the patterns that would one day become galaxies, clusters, and cosmic voids. Gravity would take those gentle undulations and amplify them, turning simplicity into structure. It's strange to think that the oldest light we can observe doesn't come from stars at all. It comes from this moment of release, when the universe took its first breath of clarity. The CMB is, in a sense, the first photograph of everything, a snapshot of the cosmos when it was still a glowing child. We study it not with our eyes, but with instruments that can detect the faint warmth of microwaves, mapping the subtle variations in temperature across the sky. Those variations are tiny, differences of only a few millionths of a degree, yet within them lies the blueprint of all structure in the universe. Slightly denser regions would later collapse under gravity to form galaxies. Slightly thinner ones would stretch into vast emptiness. It's remarkable how little difference it takes to shape everything. The entire cosmic web, the great network of galaxies that spans the observable universe, began as almost imperceptible ripples in that first clear light. As the photons streamed outward, the young universe continued to cool and expand. Hydrogen and helium filled the void, now neutral and invisible. The brilliant plasma had faded into a transparent gas. The light that once burned everywhere was now moving through space rather than trapped within it. It was as if the cosmos had exhaled after holding its breath for so long, and yet after that moment of clarity a kind of silence followed. The light moved freely, but there were no new sources of it. The universe was full of atoms, but not yet of stars. It had structure and potential only, a quiet grid of matter and dark matter slowly feeling its own gravity. For the next few 100 million years, the cosmos would remain dark, waiting for the first fires to be kindled. Even so, this moment, the moment when light first escaped, remains one of the great transitions in cosmic history. It marked the end of the universe's childhood and the beginning of its long journey toward complexity. The photons that left then will continue travelling forever, their wavelengths stretching longer and longer as space expands. In the distant future, they will fade even further, their energy redshifted beyond detection, but they will never truly vanish. The first morning light of the universe will continue to move outward, endlessly, silently. If you were to step outside on a cold, clear night and close your eyes, that silence is the closest echo of that moment you can still feel. The air around you, the darkness between the stars, is not empty. It is filled with that ancient light, cooled, stretched, and softened by time, but still present. The same glow that once filled every corner of existence now hums invisibly through every patch of sky. So much of the universe's beauty lies in what it remembers, and this light, the first light, remembers everything. The glow of creation, the calm that followed, the endless expansion that carried it here. When you look up at the stars, you're not only seeing into the past, you're standing within it, bathed in a memory older than any world. The fog has lifted, but its warmth remains. The cosmos took its first deep breath, and that breath has never stopped. When the fog of the early universe finally cleared, it left behind a vast and quiet expanse. The glow of the first light, the cosmic microwave background, had drifted outward, cooling as it travelled. What remained was a universe filled mostly with invisible hydrogen gas, spread thinly through expanding space. The brightness faded, and for the first time since creation began, the cosmos fell into darkness. This was the long night that came before the first dawn. To imagine it, think of a beach after a storm. The waves have receded, leaving a calm and silent sea. The air is still, but beneath that stillness the water is already stirring with new currents. The universe in this era was like that, outwardly serene, inwardly full of quiet motion. Astronomers call this the Cosmic Dark Age. It began around 400,000 years after the Big Bang, when light was set free and lasted for hundreds of millions of years. During this time, no stars shone, no galaxies yet existed. There were no colours, no visible light of any kind. The universe was transparent, but there was nothing to see. All around, the gas that filled space was cooling, expanding, and slowly gathering under gravity's pull. The laws that had shaped atoms and light now began shaping structure. The tiny ripples in density that had been imprinted in the cosmic microwave background, regions just a fraction denser than their surroundings, started to grow. Over millions of years, those faint differences deepened. The denser regions attracted more matter, while the emptier ones became even more empty. In the darkness, the invisible scaffolding of dark matter guided the process. Dark matter doesn't interact with light, so even though the universe was transparent, its web of gravity was unseen. It pulled ordinary matter, hydrogen and helium gas, into long, thin threads that stretched across the growing cosmos. These filaments of dark matter were the first architecture of the universe, the hidden framework on which everything else would form. To visualize it, picture dew forming along the strands of a spider's web before sunrise. The droplets, shining only when the light finally returns, trace the shape of something that was already there, unseen in the dark. That's how galaxies would later appear, luminous beads strung along invisible filaments of dark matter, revealing the web that had existed all along. But in this dark age, there were no stars yet to illuminate that web. Only hydrogen atoms floated in the cold, thin gas, colliding occasionally but too rarely to spark fusion. Space was immense and nearly featureless, expanding faster than gravity could easily gather material. For hundreds of millions of years, the universe slept in quiet anticipation. The temperature of the background radiation dropped steadily, from thousands of degrees to just a few tens, then a few. The light that once glowed brightly enough to burn the sky now hummed faintly at wavelengths far too long for human eyes to see. By the time the universe was 100 million years old, that light was already a soft murmur of warmth, drifting toward the microwaves we detect today. Even in darkness, however, there were signs of what would come. Deep in the densest pockets of gas, small fluctuations began to compress under their own weight. When matter gathers, it heats, and when it heats, it begins to glow. The first sparks were faint and rare, perhaps just a few massive clouds collapsing in the quiet. but they hinted at what was about to happen next: the birth of the very first stars. Those stars, called Population 3 stars, would be unlike anything that came after. They would form from pure hydrogen and helium, with no heavier elements to cool the gas or slow the process. As a result, they would grow enormous, hundreds of times the mass of our Sun, and burn with extraordinary brilliance. Their light would be the first to pierce the cosmic darkness, reionizing the gas and transforming the universe once again into a place of light. But that first dawn was still far away. For now, the universe was waiting. The silence was absolute. Across distances that would one day span billions of light years, only faint radio waves moved through the cold. If you could somehow have been there, drifting through the emptiness, you would not have seen a single glimmer. Yet, in every direction, gravity was working, slowly weaving the future. Dark matter continued to shape the scaffolding, pulling hydrogen along its threads. The gas began to collect into halos, invisible wells of gravity that would become the seeds of galaxies. These halos were like invisible bowls in the fabric of space, gently gathering the surrounding matter. Over time, as more and more hydrogen fell in, the density at their centres increased. Temperatures climbed. At first, the heat was too low to ignite nuclear fusion, but it was rising steadily. The collapse of matter produced turbulence, shock waves that rippled through the gas, creating eddies and filaments within the halos. Small clumps formed within the larger structures, and inside those clumps, gravity tightened its grip. The universe, still dark on the outside, was beginning to glow within. In this era, time passed slowly from our perspective, but in cosmic terms, everything was accelerating. The first stars were perhaps 200 million years away, but the groundwork was already in place. The delicate balance between expansion and gravity was reaching its turning point. Soon, light would return, and yet, there's something beautiful about this long cosmic night. It was a period of waiting, of quiet preparation, when the universe was learning how to shine. The same physics that governs the stars also governs us. Periods of calm before transformation, darkness before light. The Dark Ages were not empty, they were potential made patient. By studying this era, astronomers hope to glimpse the invisible beginnings of structure. New telescopes, like the James Webb Space Telescope, are peering deep into that ancient darkness, searching for the first galaxies that flickered to life. What they see are faint red smudges, galaxies so distant that their light has travelled for more than 13 billion years. Each of those small blurred shapes represents a moment when the dark finally gave way to brilliance. So, as you imagine that long night, don't picture emptiness. Picture anticipation, the quiet tension before a sunrise. The atoms that once drifted through that darkness now form every star, every planet, every breath. The first clear morning had given the universe light. The long dark gave it depth. And soon, from that depth, the first fires would ignite and the cosmos would open its eyes. For hundreds of millions of years, the universe drifted in silence. The fog had lifted, the light of the first morning had faded into darkness, and only the cool breath of hydrogen and helium remained. The cosmos had become a vast, invisible ocean of gas and gravity, but deep within that ocean, small ripples had begun to rise. Places where matter gathered more thickly, where the invisible pull of dark matter coaxed hydrogen into dense clouds. These clouds would soon collapse under their own weight. The long night was almost over. When the first stars formed, there were no witnesses, no eyes, no worlds, no galaxies to watch. But if you could have been there, drifting somewhere in that dark expanse, you might have seen the faintest flicker of light bloom in the distance, like a single spark appearing in an infinite night. And then, slowly, others, each one the first flame in a sleeping universe. These were the Population 3 stars and the very first generation of stars to ever exist. They were made from pure hydrogen and helium, the simplest elements born in the Big Bang. There were no heavier elements yet. No carbon, no oxygen, no iron. Nothing to help cool the gas and slow its collapse. Because of that, these stars were enormous. Some were hundreds of times the mass of our Sun. With no impurities to hinder them, they fell inward quickly and burned fiercely. They lived fast and died young. A star 100 times the mass of the Sun might live for only a few million years, a brief flash in cosmic terms. But in that short life, it shone with unimaginable brilliance, pouring out light that began to reionize the hydrogen gas around it. These first stars ended the Dark Ages. They ignited the cosmos once more, filling it with light and energy. You can think of reionization as the universe's second sunrise. During the Dark Ages, atoms of hydrogen had been neutral, their electrons and protons calmly bound together, but the light from the first stars was so intense that it began breaking those atoms apart again, stripping away the electrons, turning space into a glowing, ionized mist. The process took hundreds of millions of years, gradually transforming the dark universe into one filled with transparent light once again. Each of these massive stars was a factory of transformation. Inside their blazing cores, nuclear fusion forged heavier elements for the first time. Carbon, oxygen, silicon, iron. These were the ingredients that would later become planets, oceans, and life. When the first stars exploded as supernovae, they scattered those new elements into the surrounding space, enriching the gas that would form the next generations of stars. The universe, which had started with only 2 elements, was now learning to write its own chemistry. It's poetic to think that the atoms in your body, the carbon in your cells, the iron in your blood, the oxygen in your breath, were born in stars like these. Every living thing is a descendant of those early suns. Their brief fiery lives gave the cosmos its first colour, its first complexity, and its first promise of life. If you could have seen them, those first stars would have looked nothing like the stars in our current sky. They burned hotter, bluer, and brighter, so bright that a single one could have outshone an entire small galaxy. They formed in clusters, perhaps only a few hundred in each group, gathered in the gravitational wells of dark matter halos. Around them, hydrogen gas shimmered in ultraviolet light, forming expanding bubbles of ionized space that grew larger and eventually overlapped, lighting up the universe from within. These stars also reshaped the cosmic landscape through their deaths. The most massive among them ended in catastrophic explosions, collapsing into black holes that swallowed the surrounding gas and grew rapidly. Some of those black holes might have become the seeds of the supermassive ones we find today at the centres of galaxies. Others simply vanished into darkness, leaving behind expanding shells of glowing gas, the first cosmic remnants. In between these great bursts of light and destruction, a new kind of order began to emerge. The enriched gas from exploded stars mixed with pristine hydrogen, forming cooler, denser clouds. These clouds began to fragment and collapse again, this time producing smaller stars that could live longer, burn steadier, and cluster together. Those clusters became the first proto-galaxies, tiny, chaotic assemblies of light swirling in the darkness. The process was slow and messy. Gravity pulled, radiation pushed, and turbulence sculpted strange shapes in the clouds. The first galaxies were nothing like the elegant spirals we see today. They were clumpy, irregular, and fragile, built through endless mergers and collisions, but each one added to the growing tapestry of light. The universe was no longer silent. It was singing in starlight. As the reionization continued, space between stars became clearer again. Photons, once trapped or scattered by neutral gas, could now travel freely. The cosmic night was coming to an end. From that point onward, the universe would never be completely dark again. Wherever there was gravity, there would be new stars forming, and wherever there were stars, there would be light. In many ways, the birth of the first stars was the universe's most creative act. The Big Bang had given it existence, but the stars gave it meaning, structure, diversity, and the potential for life. Without them, the cosmos would still be a cold, featureless expanse. With them, it became a place where atoms could gather, combine, and dream. Astronomers today can't see those first stars directly. Their light is too faint, too distant, and stretched by the expansion of space into wavelengths beyond the reach of our eyes. But telescopes like the James Webb Space Telescope are beginning to glimpse their descendants, the first galaxies, just a few 100 million years after the beginning. In those faint, ancient smudges of light, we see echoes of the original fires that ended the long night. When you look up at the stars tonight, you're looking at a continuation of that same process. Hydrogen still fusing into helium, still releasing light. Every flicker of starlight in our sky is a repetition of that first cosmic spark, a note in the same ancient melody. The universe hasn't stopped igniting. It's still writing new verses in the same quiet song of fusion and radiance. The first stars lived fast, died beautifully, and changed everything. Their light reached across the vastness of space, reclaiming the darkness, painting the universe with brilliance. And when they were gone, they left behind the materials from which all later star, and we ourselves, would form. The darkness had not been wasted. It had been waiting. The dawn had come. The first stars were brief, blazing miracles, bursts of light in an otherwise silent sea. When they lived, they illuminated their surroundings with fierce ultraviolet radiation. When they died, they scattered the first heavy elements into space, seeding the gas with new ingredients for the next generation. And as they lived and died, they did something else. They began the slow, intricate work of building the first galaxies. A galaxy is, at its heart, a balance, a dance between gravity pulling inward and motion spinning outward. In those early times, that balance was still finding its rhythm. The universe was young, less than 1 billion years old, and everywhere you looked there were clouds of gas drifting through the invisible web of dark matter. Gravity tugged on those clouds, gathering them into knots and filaments. Slowly, the gas began to fall into the gravitational wells created by dark matter halos. These halos were the unseen skeletons of the cosmos, the hidden framework around which galaxies would form. As gas fell inward, it heated up, glowing faintly from compression. Turbulent flows created eddies and shocks, shaping the gas into spirals and tendrils. In some places, the gas cooled enough to collapse further, forming dense regions where new stars were born. Each cluster of stars added its own light, merging with others to form brighter, larger systems. The universe was no longer a dark ocean. It was becoming a sea filled with islands of light. These early galaxies were nothing like the graceful spirals and giant ellipticals we see in modern telescopes. They were small, chaotic, and fragile. Irregular clusters of stars held together loosely by gravity. Some may have been only a few thousand light-years across, a fraction of the Milky Way's size. Others grew rapidly by colliding and merging with neighbours, feeding on surrounding gas like living organisms. Every collision sparked new bursts of star formation, lighting up the sky with waves of newborn stars. If you could have seen it unfold, it would have looked like a slow cosmic storm. Clouds colliding, glowing, and then merging again into larger, brighter shapes. The young universe was restless and beautiful, filled with movement and change. It was still expanding, of course, the fabric of space stretching in all directions. But within that expansion, gravity was knitting the first coherent structures together. This process created what we now call the cosmic web, an enormous network of filaments stretching across hundreds of millions of light years. These filaments, made mostly of dark matter, served as the highways of cosmic evolution. Galaxies formed along them, where gas and matter flowed together at the intersections, much like cities growing at the crossroads of ancient trade routes. Between those filaments lay vast voids, immense, nearly empty regions that still exist today, where galaxies are few and far between. To picture it, imagine a delicate lace of light spread across an endless darkness, threads connecting points of brightness, each one a galaxy, each one part of a larger design. The universe, in this stage, was both intricate and elegant. The same physical laws that govern clouds, rivers, and storms on Earth were now shaping the grandest structures imaginable. As the first galaxies formed, their light began to travel across space, redshifted by the expansion of the universe. Redshift is one of astronomy's most beautiful ideas. It means that as space stretches, so too do the waves of light that move through it. The light that once left those first galaxies in the deep blue and violet range now arrives at Earth stretched into red, infrared, or even radio wavelengths. What we see through our telescopes today are echoes of that early light, softened and slowed by time itself. And now, after billions of years, instruments like the James Webb Space Telescope have finally begun to detect those faint signals. When Webb looks deep into a patch of sky that appears empty to the human eye, it finds hundreds of ancient galaxies, red, tiny, and incredibly far away. Their light has been travelling for more than 13 billion years to reach us. In those dim smudges, astronomers can see the universe as it looked only a few 100 million years after the Big Bang. Galaxies in their infancy, clumpy and irregular, yet already filled with stars. Some of these early galaxies appear surprisingly bright and mature, suggesting that the cosmos built itself faster than we once thought possible. Stars and heavy elements seem to appear almost immediately, as if the universe, eager after its long, dark night, rushed headlong into light. It's a reminder that cosmic time is not the same as human time. What seems slow to us, millions or billions of years, was to the universe an energetic youth, full of rapid growth and transformation. Inside these galaxies, new generations of stars were forming from enriched gas. Each cycle of birth and death added more complexity. The first black holes, born from the collapse of massive early stars, began to gather gas and merge, growing at the centres of galaxies. Their gravity helped shape their hosts, regulating how many stars could form. Even at this early stage, galaxies and black holes were already intertwined, influencing each other's growth like partners in an ancient dance. As these galaxies grew, they also began to assemble into clusters. Gravity pulled them together in great gatherings of hundreds or even thousands, bound within the same halos of dark matter. These clusters became the seeds of the large-scale structure we see today. Immense constellations of galaxies connected by filaments, separated by cosmic voids. Everywhere, light and shadow played against each other. Dark matter shaped the stage, ordinary matter filled it, and light revealed its form. The cosmic web was alive, a vast luminous fabric in constant motion. And though it has expanded for billions of years, that pattern remains. When we map the distribution of galaxies across the sky today, we see the same filaments and voids that began to form during this era. If you were to look at the universe from far above, from a vantage point outside time itself, you would see it glowing faintly like a living network, light pulsing along its filaments, galaxies merging and separating like cells in a vast organism. The same physics that guided those first clouds of gas still guides us, still threads through every atom and every star. The formation of galaxies marked a turning point. The universe was no longer only expanding, it was also organising itself. The raw ingredients of the Big Bang had begun to settle into patterns, and those patterns would evolve into everything we know: clusters, Superclusters, galaxies like our own, and eventually stars like the Sun and planets like Earth. Every time you look up at the Milky Way, you're seeing the end of that long transformation, the final stage of the first great cosmic construction project. What began as clouds became constellations. What began as scattered gas became home. And through it all, gravity, quiet, patient gravity, never stopped its work. The universe had learned to build, to gather, to shine. And in the depths of those first galaxies, a new mystery was already stirring. An unseen mass that held everything together, yet revealed itself only through its pull. The next chapter of creation would belong to the invisible, the strange, silent presence we call dark matter, the scaffolding beneath all light. By the time the first galaxies had taken shape, the universe was filled with light. Stars blazed across the cosmic web, and vast clusters began to form at its intersections. Yet something about the way those galaxies moved didn't add up. Their stars were spinning too quickly, their clusters holding together too tightly. According to the visible mass, the gas, dust, and starlight we could see, they should have been flying apart, but they weren't. Something unseen was keeping them bound, something invisible, silent, and strong. This invisible substance is what we now call dark matter, though the name says more about our ignorance than its nature. It doesn't shine, it doesn't absorb light, and it doesn't collide or clump in the same way normal matter does. We know it exists not because we see it, but because we see what it does, how it bends light, how it shapes galaxies, how it anchors the structure of the universe. It is the quiet architecture behind everything visible. The first clues appeared in the 1930s, when astronomer Fritz Zwicky studied galaxies within the Coma cluster. He noticed that the galaxies were moving far faster than expected, too fast to be held together by the gravity of their visible stars alone. By his calculations, the cluster needed about 10 times more mass than could be seen. He called the missing material Dunkelmaterie, or dark matter. Few people believed him at the time. The idea was strange and unsettling, suggesting that the universe was mostly made of something we couldn't detect. Decades later, in the 1970s, Vera Rubin and her collaborator Kent Ford measured the rotation of spiral galaxies with great precision. They found the same mystery repeating itself. In a galaxy like our Milky Way, stars near the outer edge should move more slowly than those near the centre, because the gravitational pull weakens with distance. But Rubin's observations showed the opposite. Stars far from the centre were orbiting just as fast as those closer in. The galaxies were spinning as though they were surrounded by vast invisible halos of mass. These halos, made of dark matter, extend far beyond the visible edges of galaxies. They are the unseen scaffolding that holds galaxies together and keeps them stable as they rotate. Without them, the stars and gas in the outer regions would drift away into intergalactic space. The Milky Way, for example, sits inside such a halo stretching hundreds of thousands of light years in every direction. We live deep inside an invisible sphere of gravity, more massive than all the stars we can see combined. But gravity's influence doesn't end there. Dark matter also shapes the cosmos on much larger scales. As light from distant galaxies travels through space, it sometimes bends and stretches slightly when passing through regions of strong gravity. This phenomenon, called gravitational lensing, acts like a cosmic magnifying glass, revealing the distribution of mass between us and those distant galaxies. When astronomers map these distortions, they find that most of the bending comes not from visible matter, but from an invisible network. Dark matter weaving through space like a transparent skeleton. Even the cosmic microwave background, that faint afterglow of the early universe, carries the fingerprints of dark matter. The tiny ripples in its temperature reflect how gravity shaped the primordial plasma before the first stars formed. When scientists compare those ripples with their models, the results point to a universe made of roughly 27% dark matter, about 68% dark energy, and only about 5% ordinary atoms. Everything we see, stars, planets, people, everything made of atoms, is just a small glowing fraction of the whole. It's humbling to realise that we exist inside a universe dominated by what we cannot see, yet the evidence for it surrounds us, not as a mystery meant to frustrate us, but as an invitation to wonder. Still, dark matter refuses to reveal itself. For decades, scientists have tried to detect it directly. Deep underground, in laboratories shielded from radiation, detectors wait for the faintest interaction, perhaps a dark matter particle bumping into an atomic nucleus. So far, those detectors have found nothing conclusive. There are many candidates for what dark matter might be. WIMPs, weakly interacting massive particles, axions, or perhaps entirely new forms of physics we have not yet imagined. Each is a whisper, a possibility. Astronomers also look for indirect signs, flashes of high-energy light that might arise when dark matter particles collide and annihilate each other. Satellites scan the skies for such signals, and though some hints have appeared, none are certain. The cosmos remains silent on the matter, holding its secret close, and yet we see dark matter's influence everywhere. Without it, galaxies would never have formed so early or so beautifully. The gravitational pull of this invisible mass gathered ordinary matter into the dense knots where stars could ignite. It shaped the large-scale cosmic web, pulling filaments of galaxies together into clusters and superclusters. Even today, the pattern of galaxies across the sky follows the invisible hand of dark matter, tracing its distribution like frost on an unseen window pane. To imagine what dark matter does, think of a stage where light and sound depend on structures hidden beneath the curtain. The audience sees the actors and hears the music, but the beams, ropes and foundations remain unseen. Yet without them, the show would collapse. That's what dark matter is to the cosmos, the quiet stage that lets the drama of galaxies play out. The presence of so much invisible matter changes how we think about our place in the universe. We live in a cosmos where the majority of reality is not luminous, not tactile, not directly measurable, at least not yet. It's a reminder that what we can see is only a thin skin of truth stretched over something vast and unknown. The beauty of science lies in how it allows us to glimpse that hidden world, not through sight, but through patterns, gravity, and light. Dark matter may be invisible, but it's not unknowable. Each discovery, each rotation curve, each gravitational lens, each ripple in the CMB brings us closer to understanding it. The darkness is not emptiness. It is structure, substance, and possibility. So, as we trace the stars across the night sky, remember that what glimmers above you is only part of the picture. For every bright star, there are oceans of unseen mass shaping its orbit. For every galaxy, an invisible halo holds it steady. And for every moment of light, there is a quiet shadow beneath it, supporting and defining its brilliance. The universe's hidden mass may never shine, but without it there would be no stars, no galaxies, no us. The unseen truly shapes the scene, and as we continue to listen to the silence between the lights, the darkness itself begins to speak. By the time the universe reached a few billion years of age, it had learned to play its own quiet symphony. The notes were galaxies and clusters, the rhythm was gravity, and the unseen hand conducting it all was dark matter. The luminous parts of the cosmos, the stars, the nebulae, the glowing arcs of light, were only the melody. Beneath them was the deep, steady baseline of invisible mass, keeping time since the very beginning. Imagine standing far outside the Milky Way, so far that you could see hundreds of thousands of galaxies at once. If you could turn their light into sound, you might hear something like a slow, resonant chord, the low hum of gravity binding matter together. That harmony wasn't written overnight. It emerged through countless interactions, Gravity pulling matter into filaments, collisions igniting stars, supernovae scattering metals that would one day become planets. Every movement, every flicker of light was part of an evolving cosmic score. At first glance, the universe might seem chaotic, galaxies crashing together, stars exploding, gas clouds tumbling through space. But when scientists run vast computer simulations that follow billions of particles across billions of years, a pattern appears. The chaos resolves into music. Matter, both visible and dark, flows along invisible filaments that stretch for hundreds of millions of light years. These filaments weave together into a three-dimensional web, the same cosmic web that was seeded by tiny ripples in the early universe, magnified by gravity's patient pull. In those simulations, each speck of dark matter acts like a note in the orchestra. Alone, it's meaningless. But together, trillions of them create harmony, the grand architecture we see today. Galaxies form where the notes crescendo at the intersections of filaments. Clusters form where several melodies overlap. Even voids, the empty spaces between, play their role, the pauses that make the music breathe. When astronomers compare these simulations to real observations, to the maps of galaxies made by surveys like the Sloan Digital Sky Survey, they find a striking match. The cosmic web we simulate in computers looks nearly identical to the one we observe in the sky. It's as if the universe followed a score written in mathematics, one that we're only now learning to read. The melody of structure is universal. The unseen shapes the seen, and the pattern repeats from the smallest scales to the largest. Galaxies themselves are living instruments within that symphony. Their spirals and ellipses are shaped by gravity, but also by the feedback of their own stars. When massive stars explode as supernovae, they push gas outward, sculpting the galaxy's form. When black holes feed on surrounding matter, they release jets of energy that can regulate star formation across entire regions. Each galaxy is a self-regulating system, improvising around a central theme: creation, destruction, renewal, repeated over cosmic time. Dark matter's role in this composition is subtle, yet profound. It doesn't interact with light or ordinary matter except through gravity, but that gravity determines where gas can settle and form stars. Without dark matter's invisible scaffolding, galaxies would be sparse, scattered, and short-lived. The unseen mass provides the frame that lets light gather, just as the tension of a drum skin gives rhythm to air. On smaller scales, dark matter also helps explain the way galaxies cluster together. Gravity doesn't act in isolation. Each galaxy pulls on its neighbours, drawing them into groups and clusters. These clusters, some containing thousands of galaxies, are the largest bound structures in the universe. Between them lie immense voids, regions so empty they contain fewer atoms than the average human breath. Yet even these emptinesses are defined by dark matter's hand, shaped by its quiet pressure on the expanding fabric of space. Astronomers studying the growth of these structures often describe it as a kind of cosmic conversation, a call and response between dark matter and dark energy. Dark matter pulls things together, dark energy pushes them apart. For billions of years, dark matter led the melody, building structure through gravity's pull. But in the last few billion years, a new counterpoint began: the accelerating expansion of space. That new force, dark energy, now adds its own quiet tension to the song. You can think of the cosmic web as a frozen symphony, a piece that's still playing but whose themes were established long ago. The deep filaments connecting clusters are like the bass lines that never change, anchoring the rhythm. The galaxies and stars are the changing melodies, sparkling and fading with time. The silence between them, the vast voids, gives the music its grandeur. There's beauty in knowing that we can see and even simulate this harmony. Astronomers use supercomputers with thousands of processors to model the evolution of the universe. They begin with tiny ripples in density, no larger than 1 part in 100,000, drawn from measurements of the cosmic microwave background. Then they let the laws of gravity and physics play out over billions of virtual years. The result is astonishing. Filaments, clusters, and galaxies arise naturally, just as we observe them. In these simulations, you can even see the influence of dark matter directly. Though invisible, it shapes everything. Its presence bends the paths of galaxies, controls their speed, and dictates their fate. When scientists render these models into images, they look like glowing neural networks, threads of light linked by bright nodes, eerily similar to the structure of the human brain. It's as if the universe and our own minds share a geometry of thought, connections and voids, pattern and pause. From this perspective, the cosmos feels less like a machine and more like a piece of music, a living, breathing system of harmony and balance. Every law of physics, from gravity to quantum fluctuations, contributes a note. The universe is not random, it's rhythmic. And though we cannot hear it directly, its echoes everywhere, in the distribution of galaxies, in the vibration of atoms, even in the beating of our hearts. To understand the universe's structure is to recognize that the invisible can be more real than the visible. Dark matter may never glow, but it conducts the light of stars like a cosmic maestro. Galaxies may seem isolated, but they play in concert, moving to a rhythm that began nearly 14 billion years ago and still continues today. And just as in music, the beauty lies not only in the notes, but in the spaces between them, the voids, the silences, the moments where gravity pauses before pulling again. The symphony of structure is still unfolding, yet even now a new instrument has entered the stage, one that will change the tempo of the cosmic song, for as dark matter pulls, another even more mysterious force pushes, a gentle, invisible pressure that accelerates the universe's expansion. Its melody is softer than gravity's, but its reach is infinite. The next movement in the cosmic symphony belongs to dark energy. For most of the 20th century, astronomers assumed that the expansion of the universe, the stretching of space itself, was slowing down. It seemed reasonable. After all, gravity pulls everything together, and the more matter there is, the stronger the pull should be. Like a ball thrown upward, the universe might rise for a while, but eventually it would slow, perhaps even fall back in on itself. For decades, this idea quietly shaped our view of cosmic history. The universe expanding, coasting, cooling, but gradually losing its momentum. Then, in the late 1990s, a quiet revolution began. Two groups of astronomers set out to measure how fast the universe was slowing down. They used a special kind of exploding star, a Type 1a supernova, as a standard candle. These explosions, triggered when dying white dwarf stars reach a critical mass and collapse, always release about the same amount of light. Because their brightness is predictable, they act like cosmic streetlights. By comparing how bright they appear from Earth to how bright they should be, scientists can calculate their distance. If they could measure how far away these supernovae were and how fast their galaxies were receding, they could determine whether the universe's expansion was decelerating. They expected to find that the distant galaxies were moving away a bit slower than they had in the past, their speed tempered by the pull of all the matter within them. But the data told a different story. When the light from those ancient supernovae was analysed, it revealed that the galaxies hosting them were not slowing down at all. They were speeding up. The expansion of the universe was accelerating, as if some unseen force was gently pushing space apart. This discovery, announced in 1998, changed cosmology forever. The teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, had uncovered evidence of something completely unexpected. A force that seemed to work in opposition to gravity. Whatever it was, it filled all of space evenly. and its effect grew stronger as the universe expanded. It wasn't matter, dark or otherwise. It wasn't light or radiation. It was something new, something hidden in the vacuum itself. Scientists called it dark energy, and to describe it mathematically they used a Greek letter, lambda, the same term that Albert Einstein had once added to his equations of general relativity. He had invented lambda as a cosmological constant, a balancing term meant to keep the universe static. Later, when the expansion was discovered, he removed it, calling it his greatest mistake. And yet, decades later, that same symbol returned, now with a new meaning, not a way to keep the universe steady, but a way to explain why it was speeding apart. It's important to note that dark energy isn't a force in the usual sense. It doesn't push galaxies through space like a wind. Instead, it seems to be a property of space itself, a gentle pressure that makes the fabric of the cosmos expand faster over time. The more space there is, the more of this energy exists, and the more expansion it drives. It's like a whisper that grows louder the farther it travels. Today, we estimate that dark energy makes up about 68% of the total energy content of the universe. Dark matter accounts for roughly 27%, and all the ordinary matter, everything made of atoms from stars and planets to clouds and people, contributes only about 5%. In other words, everything we can see is just the bright foam atop a vast invisible ocean. The cosmos is not mostly stars or galaxies, but mostly dark, not in the sense of emptiness, but in the sense of mystery. To imagine dark energy, think of the spaces between galaxies as soft fabric. For billions of years, gravity has tried to pull that fabric together, while dark energy has been stretching it apart. For a long time, gravity dominated. Galaxies formed, clusters grew, and the universe built its grand architecture. But about 5 billion years ago, the balance began to shift. The expansion reached a scale where dark energy became stronger than gravity's hold. From that moment on, the universe's growth began to accelerate. This acceleration is subtle on small scales. Within galaxies, gravity still rules. The Milky Way won't drift apart, neither will our solar system. Dark energy acts only across the vast stretches of intergalactic space, where its influence can overcome the faint attraction between distant clusters. Its effect is quiet but relentless. Each billion years, the spaces between galaxies stretch a little faster, their light sliding to redder and redder wavelengths as they drift away. The discovery of dark energy forced scientists to rethink the ultimate fate of the cosmos. If the acceleration continues, then distant galaxies will keep moving away from us, faster and faster, until their light fades completely. In the far future, only the closest galaxies, those bound to our local group, will remain visible. The rest will vanish beyond the horizon of observation, their light forever unable to reach us. The night sky will grow emptier, not because the stars are gone, but because space itself has carried them beyond sight. There are many theories about what dark energy might be. Some think it is truly constant, an intrinsic energy of empty space that never changes. Others suspect it might evolve over time, perhaps linked to a field similar to the one that drove inflation in the earliest moments after the Big Bang. Some imagine it as a hint of new physics, a sign that our understanding of gravity is incomplete. But for now, it remains the largest question in cosmology. Not a problem to be solved quickly, but a mystery to be lived with, patiently explored in data and imagination alike. It's humbling to think that the force responsible for the universe's acceleration was discovered not through new technology or giant experiments, but through careful listening, through studying the light of dying stars scattered across billions of years. The universe revealed its secret through the same medium that carries all its stories, light stretched by expansion, time written in brightness and colour. When we look at the stars, we see gravity's art, light pulled inward, forming galaxies and constellations. When we look at the darkness between, We see dark energy's art, space itself unfolding, carrying those lights farther apart. Together they compose a balance so vast it almost feels deliberate. The universe is expanding, accelerating, and aging all at once, a grand, slow dance between attraction and release. And in the midst of it all, we exist. Tiny, temporary forms made from that rare 5% of luminous matter. We are the bright trace in a quiet, overwhelming whole, aware enough to notice the pattern. Perhaps that's what makes the discovery of dark energy so beautiful. It reminds us that mystery isn't absence, it's presence, too wide to measure and too deep to name. The same quiet force that pushes galaxies apart also leaves us with wonder, the sense that even in the vast silence of space, something still breathes. When astronomers first realized that the universe was accelerating, they were astonished. But astonishment in science is only the beginning. The next step is always to measure, to test, to verify whether the melody you think you hear is truly part of the cosmic song. So, over the past quarter century, scientists have built an intricate orchestra of methods to listen to the expansion of the universe with increasing precision. They measure not just light, but distance, motion, and time itself, each one a different instrument playing the same quiet tune of an expanding sky. The first and most familiar of these instruments remains the supernova, those same Type 1a explosions that revealed dark energy in the first place. They act as standard candles scattered across billions of light years, each one a tiny beacon of known brightness. By comparing how faint a distant supernova appears to how bright it should be, astronomers infer its distance. When they pair that distance with the redshift of the galaxy it lives in, how much its light has been stretched by expansion, they can trace the speed of the universe's growth across time. The farther away the supernova, the older the light, and the earlier the era it shows. By collecting hundreds, then thousands of them, scientists can reconstruct a kind of film reel of the universe's expansion, frame by frame, from its youth to its present. And when that film plays back, it shows not a constant tempo, but a gradual acceleration, a rising pitch that began about 5 billion years ago, when dark energy started to dominate the cosmic rhythm. But supernovae are only one piece of the melody. To cross-check them, astronomers use another subtle signature written in the large-scale distribution of galaxies, the baryon acoustic oscillation, or BAO for short. The name may sound technical, but the idea is simple. In the early universe, sound waves rippled through the hot plasma of matter and radiation. When the universe cooled and atoms formed, those waves froze into the distribution of matter, like ripples permanently imprinted in the surface of a frozen pond. Today, galaxies tend to be spaced with a preferred separation that reflects those ancient sound waves. By measuring this characteristic scale, the average distance between galaxies connected by that ripple, astronomers can gauge how the expansion of space has stretched since those waves first formed. The BAO signal acts like a cosmic yardstick, one that remains consistent over billions of years. When its measurements align with those from supernovae, we gain confidence that the picture is correct, that the universe is indeed expanding faster than gravity alone can explain. Then there's gravitational lensing, another exquisite tool. Light from distant galaxies doesn't travel in straight lines. It bends slightly when it passes near massive objects, such as clusters of galaxies or halos of dark matter. This bending distorts the images of background galaxies, stretching them subtly. By mapping these distortions across the sky, astronomers can measure how matter, both visible and invisible, is distributed through space, and how that distribution changes over time. Why does this matter for dark energy? Because as space expands, the growth of structure slows down. If dark energy is pushing the universe apart faster, it also prevents matter from clumping as quickly under gravity. By studying how the cosmic web evolves, how dense regions grow or fail to grow, scientists can indirectly infer how strong the expansion is and how it has changed through cosmic history. It's like watching a tree's growth rings to infer the seasons it has lived through. Another key instrument in this symphony is the cosmic microwave background, that ancient afterglow from when the universe was only 380,000 years old. Tiny variations in its temperature reveal how matter and energy were distributed back then. By comparing the CMB's precise pattern with today's observations of galaxies and clusters, cosmologists can model how the expansion has evolved over the last 13.8 billion years. All these measurements, supernova, BAO, lensing, and CMB, form a vast web of evidence. When fitted together, they create a model called lambda cold dark matter, or LCDM for short. Lambda represents dark energy, and cold dark matter refers to the invisible matter that forms the universe's framework. Despite its simplicity, this model describes nearly everything we can measure: the formation of galaxies, the geometry of space, the composition of the cosmos, and even its age. It's like a harmony of many instruments agreeing on one melody. In the LCDM picture, the universe began as a hot, dense sea of particles and light, expanded and cooled, formed galaxies and stars, and then entered an era dominated by dark energy. It is spatially flat, meaning that parallel lines would never converge or diverge, a geometry consistent with what we observe. The numbers derived from this model fit countless independent observations: the clustering of galaxies, the ages of stars, the shapes of supernova light curves, and the ripples in the CMB. For a few decades now, it has been the cosmic equivalent of a grand unified symphony, remarkably simple and remarkably precise. Yet even perfect harmony can hide a subtle discord. In recent years, as our instruments have grown sharper and our data more precise, small discrepancies have begun to appear, tiny disagreements between different ways of measuring the same expansion rate. They are small but persistent, and they whisper that there may be more to the story than we yet understand. Some scientists suspect that the tension arises from systematics, tiny calibration differences between telescopes, or assumptions built into how we interpret certain types of light. Others wonder if the discord hints at something deeper, perhaps new physics, new particles, or a form of dark energy that changes over time. The universe, it seems, is once again inviting us to listen more closely. But before we face those mysteries, it's worth pausing to appreciate how far our measurements have brought us. The fact that human beings, creatures of dust, light, and curiosity, can measure the acceleration of space itself, billions of light years away, is extraordinary. We do it not through force, but through patience, by studying the flicker of stars, the hum of microwaves, the spacing of galaxies, and the bending of light. The universe reveals its secrets to those who learn to listen in many wavelengths. When you look up at the night sky, you are witnessing this expansion in slow motion. Every star, every galaxy, every particle of light is part of that quiet drift. We don't feel it because gravity binds our local world too tightly. But over immense distances, the stretching of space is real. A cosmic breath that grows wider with every passing second. In a way, the universe is both still and moving. On small scales, the stars circle, the planets orbit, and gravity holds its familiar sway. On the grandest scales, everything is receding from everything else, carried along by an invisible current. Measuring that current and that gentle acceleration is one of humanity's most profound achievements. It tells us not just where we are in the cosmos, but what kind of universe we inhabit. One that continues to expand, to surprise, and to invite wonder. The sky is not still. It is moving, breathing, growing. And though our tools are limited, our curiosity is not. The more precisely we measure, the more quietly the universe hums its secrets back to us. A reminder that even in apparent harmony, there may always be a note we've yet to hear. For more than a century, ever since Edwin Hubble first measured how galaxies drift apart, astronomers have been trying to calculate one of the most important numbers in all of cosmology, the Hubble constant, and the current rate at which the universe expands. It's a deceptively simple idea. If you know how fast galaxies are receding from us and how far away they are, you can measure how quickly space itself is stretching. From that, you can estimate the age of the universe, how long it's been expanding since the Big Bang. In principle, the math is straightforward. In practice, the universe seems to have written two answers. The tension began quietly. On one side, scientists who studied the early universe using data from the cosmic microwave background. That faint afterglow left over from when the cosmos was just 380,000 years old arrived at one number, about 67 kilometers per second per megaparsec. That means that for every million parsecs, or roughly 3 million light years, galaxies appear to move away from us 67 kilometers faster. On the other side, researchers studying the nearby universe, observing supernovae and pulsating stars called Cepheids, came up with a higher value, around 73 kilometers per second per megaparsec. Both sides were confident in their data, and both used rigorous independent methods. The disagreement was small, only a few percent, but in a field where precision is everything, that difference has sparked one of the most intriguing puzzles in modern science. To understand why this matters, imagine trying to calculate your age by measuring how fast you're growing. If one method said you were 13 years old and another said you were 15, you'd know that something in your reasoning needed to be checked. In the same way, the universe seems to be telling two versions of its age. According to the lower value, inferred from the cosmic microwave background, the universe is about 13.8 billion years old. According to the higher value, measured from local observations, it might be closer to 12.5 billion. That's a difference of over 1 billion years. Not enough to change the story entirely, but enough to hint that we might be missing a crucial detail. Some scientists suspect that the problem lies in the calibration of our measurements. To find distances in the local universe, astronomers rely on a cosmic distance ladder. They start with objects whose distance we can measure directly, like nearby Cepheid stars, whose brightness varies in a predictable rhythm. Then they use those stars to calibrate more distant standard candles like Type 1a supernovae. But each step of the ladder carries uncertainties, small biases that might add up. Others think the issue might not be in the nearby universe, but in our interpretation of the early one. The number 67 comes from models fitted to the cosmic microwave background, using the LCDM framework, lambda-cold dark matter, which assumes dark energy is constant and dark matter is cold and slow-moving. If any of those assumptions are incomplete, even slightly, the inferred expansion rate could be off. And then there's the possibility that neither side is wrong, that the universe truly behaves differently across time. Some cosmologists propose that the Hubble constant might not be constant after all. Perhaps dark energy has changed its strength over the ages. One idea, called early dark energy, suggests that in the first few 100,000 years after the Big Bang, a brief burst of repulsive energy accelerated expansion slightly more than expected, leaving a subtle imprint on the universe's structure and on the CMB. That early acceleration would make the cosmos look a bit older when viewed through ancient light, and a bit younger when measured through nearby galaxies. Another possibility is that new particles, perhaps an undiscovered kind of neutrino or other light species, influenced the universe's evolution in ways we haven't yet accounted for. Adding such particles would change how fast the early universe expanded, shifting the calculated value of the Hubble constant to better match local measurements. Each new explanation opens new questions. If there was early dark energy, what caused it to fade? If there were extra particles, where are they now? If gravity behaves differently on cosmic scales, how does that reconcile with the precision of relativity tested on smaller scales? The more precisely we measure the cosmos, the more it asks of us. The Hubble tension, as this discrepancy is now called, might seem like a technical detail, a disagreement over a few numbers and units. But in reality, it touches the foundations of cosmology. It asks whether the model that has served us so well, LCDM, is truly complete or merely an approximation. For decades, that model has been the elegant harmony of the universe, tying together dark matter, dark energy, and cosmic history. But perhaps, like any great symphony, it contains notes we haven't yet heard clearly. When scientists talk about this tension, they do so with both excitement and humility. On one hand, they're thrilled. True progress often begins with small contradictions. On the other hand, they tread carefully, knowing that nature doesn't yield its secrets easily. The difference might vanish with better data, or it might lead us to a new understanding of physics. Either way, it reminds us that the universe is not a solved equation. It's a conversation still unfolding. There's something almost poetic about this. The universe expanding at two speeds, depending on how you listen. The ancient light of the cosmic microwave background tells the story of its youth. A calm, consistent rhythm set billions of years ago. The bright, recent light of nearby stars and galaxies tells the story of its adulthood. A slightly faster tempo, as though the universe has picked up its pace with age. Two melodies, both true in their own way, blending into a deeper mystery. Even if we never fully resolve the Hubble tension, the process of trying teaches us something profound about science itself. Precision is not the same as understanding. You can measure the heartbeat of the universe to many decimal places and still not know what gives it life. The goal of cosmology is not only to calculate, but to listen, to notice when the rhythm changes, and to ask why. So when astronomers compare those two values, 67 and 73, they're not just debating numbers, they're hearing the subtle hesitation in the universe's song, a pause that hints at another verse yet to be written. Perhaps one day, a new generation of telescopes will find the missing note, or perhaps the discord will remain, a reminder that even our best models are temporary bridges between ignorance and insight. The cosmos has always taught through contradiction. It hides truth inside paradoxes, showing us that every measurement, every observation is a mirror of both what is and what we still don't know. And as long as there are two speeds, two melodies, two interpretations of expansion, the universe continues to do what it does best, make us wonder. Long before the first stars flickered into life, before galaxies swirled, and before light could even travel freely, the universe left behind a collection of quiet, invisible relics, echoes of its earlier seconds. Most of them are faint, nearly undetectable, but together they tell the hidden story of how the cosmos grew from chaos into order. These relics are not the loud, blazing signals of creation, but the soft afterthoughts, the whispers that linger long after the symphony's opening crash. One of these ancient relics is the cosmic neutrino background, a ghostly sea of particles that has filled space since the universe was about 1 second old. To picture what that means, imagine the cosmos then, a dense, glowing soup of particles, all colliding, merging and scattering faster than thought. Neutrinos, tiny, nearly massless particles, moved among them, interacting only through the weakest forces of nature. As the universe expanded and cooled, those interactions faded and the neutrinos slipped free, streaming outward at nearly the speed of light. Since then, they've been travelling endlessly, untouched by stars or dust, a silent chorus from the first heartbeat of time. Today, those same neutrinos are everywhere, passing through you right now by the trillions each second. They go through planets, stars and galaxies as easily as light passes through glass. Because they hardly ever interact, they're almost impossible to detect directly. But their presence is known through their influence, subtle fingerprints on the structure of the cosmos. When scientists model how galaxies form, they find that neutrinos, despite their tiny mass, slightly slow down the growth of large-scale structures. It's as though these ghostly travellers act as a fine mist over the cosmic landscape, softening gravity's grip just a little. The temperature of the cosmic neutrino background is only a few degrees above absolute zero, around 1.9 Kelvin, colder even than the cosmic microwave background's 2.7. That faint difference marks their age. They decoupled from matter before photons did, escaping the cosmic plasma earlier, and so have cooled longer. Though we can't yet see them directly, their effects are imprinted in the CMB and in the clustering of galaxies. It's extraordinary to think that we can infer the existence of a relic from the universe's first second by looking at the patterns of light in the sky today. But the neutrino sea is only one whisper among many. Another relic lies hidden in the very existence of matter itself, the asymmetry between matter and antimatter. The laws of physics, as far as we can tell, treat both nearly equally. When particles and their mirror opposites meet, they annihilate, leaving behind pure energy. By that logic, the universe should have produced equal amounts of each, and thus should have destroyed itself entirely in a flash of radiation, leaving nothing but light. And yet, that didn't happen. Somehow, for every billion pairs of matter and antimatter that vanished, one extra particle of matter survived. That tiny imbalance, 1 in a billion, is why there are galaxies, planets, and people at all. This cosmic preference for matter over antimatter is known as baryon asymmetry, and the process that created it, baryogenesis, remains one of the universe's most delicate mysteries. For it to occur, 3 special conditions had to be met. First, certain physical laws had to allow processes that violate the conservation of baryon number, essentially ways to create more matter than antimatter. Second, those processes needed to break a symmetry called CP symmetry, meaning that the laws of physics had to treat matter and antimatter just slightly differently. And third, the universe had to be out of thermal equilibrium, cooling or expanding rapidly enough for these tiny imbalances to accumulate rather than cancel out. In laboratory experiments, we've seen hints of CP violation in the behaviour of subatomic particles like kaons and B mesons, but not enough to explain the enormous asymmetry that exists. Whatever mechanism tipped the balance must have operated in the earliest instance of time, perhaps linked to energies far beyond what our accelerators can reach. Some theories suggest that neutrinos themselves, those same ghostly relics, may have played a role. If their heavier ancestors behaved differently from their mirror versions, they might have seeded the imbalance we now see. That idea, called leptogenesis, connects the faintest particles in existence to the grandest fact of all, that there is something instead of nothing. It's humbling to think that our existence hinges on a statistical whisper. Out of every billion reactions, just one leaned ever so slightly in favour of matter. That 1 in a billion bias wrote the entire script of cosmic history. The formation of atoms, stars, planets, and life. Every breath you take is in a sense a continuation of that ancient victory, that cosmic improbability. The universe didn't have to choose matter, but it did, and here we are. There are other relics too, more speculative but equally haunting. Some scientists believe there may still be traces of primordial gravitational waves, ripples in space-time generated during the universe's earliest moments, perhaps during inflation. If these waves exist, they would carry information from a time even before light could travel, a direct signature of the universe's birth. Detecting them would be like hearing the faint vibration of creation itself. So far, these waves have eluded us, but the search continues with instruments sensitive enough to measure distortions smaller than a fraction of a proton's width. Each of these relics, the neutrino sea, the matter asymmetry, the potential gravitational waves, reminds us that the universe is not only made of what we see, but also of what we almost lost. It's built on narrow escapes and delicate imbalances, on fluctuations that could have gone another way. That fragility gives its story a strange beauty. Creation was not inevitable, it was improbable, and yet it happened. Modern cosmology is, in many ways, a science of whispers. We don't study the loud events, the explosions, the flashes, the grand displays of energy, as much as we study their aftermath. We read the sky like a palimpsest, tracing faint imprints left by moments we can never revisit. Every new measurement, every particle detected, is an echo returning from the edge of understanding. When we study the cosmic neutrino background, or the imbalance between matter and antimatter, we are not simply cataloguing numbers. We are listening to the universe's memory. We are hearing the faint reverberation of choices made long before time took shape as we know it. Perhaps that's why humility is such an essential part of cosmology. We are working with the faintest clues, with radiation cooled almost to nothing, with particles that pass through entire planets unnoticed, with probabilities that favoured existence by only 1 part in a billion. We study whispers, not roars, and yet those whispers tell us that even in the stillness of space, creation continues to speak. If the universe is a story written in light, then these hidden relics are the spaces between the words, quiet, almost invisible, but vital to the meaning. They remind us that what seems empty often holds the deepest truth, and that every silence carries a trace of what once was loud. Somewhere, even now, the ancient neutrinos still travel, across galaxies, through stars, through you. They are the oldest travellers of all, carrying with them the faint memory of a universe just 1 second old. You can't hear them, but if you could, their song would be the softest hum imaginable, the sound of the cosmos remembering itself. The Big Bang is often described as the beginning of everything, a single flash, an explosion out of nothing. But that picture, however vivid, isn't quite right. The Big Bang wasn't an explosion in space, it was an expansion of space. There was no centre, no edge, no fireball blooming into emptiness. Space itself stretched, carrying everything within it, and as it expanded, the universe cooled, light separated from matter, and the story of time began to unfold. Still, there's a question that never quite fades. If the Big Bang wasn't an explosion of matter into pre-existing space, what was it expanding into? And what, if anything, came before? For decades, cosmologists have approached these questions not with absolute answers, but with humility, and with a sense that perhaps some questions are better understood as limits rather than lines to be crossed. The simplest and most successful model, LCDM, lambda cold dark matter, describes what happened after the first fraction of a second. It traces how the universe expanded, cooled, and evolved into the web of galaxies we see today. But it doesn't say where that first moment came from, or what set the expansion in motion. To explore those ideas, scientists have imagined other possibilities, not to replace the Big Bang, but to ask what might lie just beyond its horizon. One of the earliest alternatives was the steady-state model, proposed in the mid-20th century by astronomers Hermann Bondi, Thomas Gold and Fred Hoyle. In their vision, the universe had no beginning or end. It expanded, yes, but as space grew, new matter continuously appeared, keeping the overall density constant. In this eternal cosmos, galaxies would form, drift apart, and new ones would take their place. A universe without birth or aging, endlessly renewing itself. It was a bold idea, elegant and strangely comforting, but it couldn't survive the evidence. When the cosmic microwave background was discovered in 1965, that faint afterglow left over from a hot, dense past, the steady, state model fell silent. The light itself proved that the universe once had a temperature so high that atoms couldn't exist. The cosmos wasn't eternal in its current form. It had undeniably changed. Later, other theories arose trying to go deeper than the Big Bang. Some imagine that the universe might be part of a cycle, expanding, contracting, and then expanding again. In these cyclic or bounce models, each Big Bang is not the first, but one of many breaths in an infinite cosmic rhythm. When the universe expands too far, gravity eventually wins, pulling everything back together into a big crunch. Then, from that collapse, a new expansion begins. Time, in this view, loops endlessly, with no true beginning or end, only transitions. Modern versions of this idea are more subtle. The ekpyrotic model, for instance, suggests that our universe could be a three-dimensional surface, a brain, embedded in a higher dimensional space. In this picture, the Big Bang might have been the result of two such brains colliding, releasing enormous energy and creating the hot, dense conditions we know. The concept stretches imagination, but it arises naturally from certain interpretations of string theory, where extra dimensions and vibrating fields replace the simple geometry of space. Another, even more abstract idea comes from conformal cyclic cosmology, proposed by mathematician and physicist Roger Penrose. In this view, the universe doesn't bounce but fades. As it expands and cools, all matter eventually decays and black holes evaporate, leaving behind a thin, uniform sea of radiation. In that empty, scale-free future, the distinctions between small and large, between near and far, disappear. Without any particles left to mark time or distance, the universe becomes timeless again. At that point, Penrose argues, it could seamlessly transition into a new Big Bang, beginning the next aeon. Each universe's end becomes the next one's beginning, not a circle, but a chain of cosmic rebirths stretching into infinity. There are other hypotheses too, some based on quantum cosmology, where space and time themselves emerge from deeper laws we don't yet fully grasp. In this view, the Big Bang wasn't the birth of the universe, but the moment when our familiar notions of time and space became meaningful, when quantum possibilities condensed into a single unfolding reality. Before that, the question of before may simply not apply, because before assumes a timeline that didn't yet exist. Stephen Hawking once offered a simple analogy. Asking what came before the Big Bang might be like asking what's north of the North Pole. The question feels natural, but doesn't have meaning in the same way. Space and time, he suggested, are not an infinite stage but part of the story itself. They may have boundaries but not edges, limits where the rules change rather than places where things stop. What's striking in all these ideas is not their certainty, but their willingness to explore. Each model, whether cyclic, quantum, or multi-dimensional, is a way of testing our imagination against reality. None are complete, and perhaps none are final. But they show that cosmology isn't only about describing what happened. It's about listening for what might still be happening beyond our view. In the end, these speculations share something deeper than data. They reveal the human need to understand our origins. Whether we imagine the universe as eternal, cyclic, or emergent, we're asking the same question in different forms. Not just, how did it begin? But, why is there anything at all? That's a question physics can approach but never fully answer. Equations can describe the behavior of space and time, but they cannot explain why the equations exist. Perhaps that's why the mystery endures. The Big Bang remains a boundary, the horizon of what we can observe and what we can meaningfully describe. Beyond it may lie other realms, other cycles, other beginnings, or perhaps not. Perhaps the true wonder lies in the fact that a universe born from chaos can give rise to calm reflection, that beings made of stardust can ponder the silence that preceded the stars. Maybe the right way to think about the Big Bang isn't as an explosion, or even as an event, but as a transition, the universe shifting from potential to presence. Before that moment, the laws of physics might have existed only as probabilities, like notes waiting to be played. Then, in an instant beyond measure, the music began, And we, billions of years later, are still listening. Every atom in your body, every photon of light that touches your eyes is part of that same unfolding song. Whatever before may mean, it has already become now. The story continues quietly within and beyond you. If the story of the universe has a beginning, it also has an ending, though not the kind of ending we might expect. There will be no final explosion, no collapse into fire, no dramatic curtain call. Instead, the cosmos will drift towards silence, expanding into a state of quiet that deepens so slowly we would hardly notice it even over 1 trillion lifetimes. The same expansion that began at the Big Bang, that gentle stretching of space, will continue, guided by the quiet hand of dark energy. The universe will grow older, colder, and lonelier, and yet, in its own way, it will remain beautiful. Right now, the night sky still glows with the combined light of hundreds of billions of galaxies, but that view will not last forever. As space continues to expand faster and faster, distant galaxies will drift beyond what astronomers call the cosmic horizon, the boundary beyond which their light can never reach us, no matter how long we wait. Each year, more galaxies slip quietly beyond sight, their light stretched into invisibility by the expansion of space itself. In about 100 billion years, the universe will look very different. The Milky Way and the Andromeda Galaxy, currently separated by more than 2 million light-years, will have merged into a single, massive elliptical galaxy, sometimes nicknamed Milk-Dromeda. Around it will orbit a handful of smaller companions, but the rest of the universe will have faded away. Distant galaxies will have vanished from view, their light redshifted so far into the infrared that even the most powerful instruments could never detect it. To future astronomers, the sky will seem almost empty, and the cosmic story will appear much smaller than it truly is. Stars, too, will change. The most massive ones will live fast and die young, ending their lives in spectacular supernovae or collapsing into black holes. Smaller stars like our Sun will burn slowly, shining for tens of billions of years before fading into cool, dim embers called white dwarfs. As the universe ages, star formation will slow, then stop. The raw gas that fuels new stars will be used up or locked away in dead remnants. Over time, the cosmos will transition from an age of light to an age of afterglow. Even that afterglow will fade. White dwarfs will cool into black dwarfs, radiating no heat or light. The great galaxies will grow dim, filled with cold remnants and dark matter halos. Black holes will remain, silently consuming the matter around them, growing heavier but also rarer as their fuel runs out. The stars will die, one by one, until only darkness remains between the fading sparks. But darkness, in this far future, won't mean emptiness. Black holes, though invisible, will dominate the stage for a long time. They will merge occasionally, releasing bursts of gravitational waves that ripple through space like the faint chords of a song remembered by no one. Eventually, even they will begin to fade, over timescales so vast they challenge imagination. On the order of 10 to the power of 100 years, black holes will slowly evaporate through Hawking radiation, releasing their stored energy as a final whisper of heat. When the last black hole disappears, the universe will enter what physicists call the heat death, or the big freeze. Space will continue to expand, but there will be nothing left to illuminate it. All energy will be evenly spread, every difference smoothed out. No star will shine, no planet will orbit, no event will break the stillness. The cosmos will have reached perfect balance, and therefore perfect silence. It sounds desolate, but there's a strange peace in this vision. The universe began as a burst of energy, full of motion and change. Its end, if we can call it that, is a return to stillness, a cooling back into equilibrium. The journey from chaos to calm is not unlike the rhythm of a single human life. A fiery beginning, a long unfolding, and a quiet rest. And yet, even in that distant silence, something of the universe will endure. Energy cannot truly be destroyed, only transformed. Every particle that has ever existed will have left its trace somewhere, in the shape of space, in the faint curvature of gravity, in the memories written into matter. The atoms that make you, for instance, will not vanish. They will drift apart, carried into the deep future, dispersed across unimaginable distances. They will never again take the same form, but they will still exist. Tiny echoes of a brief moment when the universe looked inward and wondered about itself. If we could somehow step into that far-off age, when the stars are gone and even black holes have faded, we might find that the universe has not truly ended, but simply changed its language. Instead of light, it will speak in the faint quantum hum of empty space. Instead of galaxies, it will express itself in the geometry of expansion. The cosmos will not stop breathing. It will only breathe more slowly, exhaling into eternity. It's tempting to call that the end, but perhaps that word is too sharp for something so gradual. The universe doesn't end with a bang or a crash. It fades, like the last note of a long song. And perhaps, somewhere beyond the limits of our understanding, a new melody might begin, a new expansion, a new cycle, another version of existence taking shape from the quiet. If cosmology teaches us anything, it's that stillness and change are two sides of the same mystery. For us, here and now, that vast future is both distant and intimate. The same laws that will govern the universe's fate also govern the atoms in your breath, the light in your eyes, the warmth in your hands. You're made of elements forged in the hearts of long-dead stars, and those atoms still obey the same laws that shape galaxies. In that sense, the expansion of the universe isn't just something happening out there. It's happening within you too. Every breath is a small echo of the universe's own quiet rhythm. So when you look up at the stars, you're looking not just backward in time, but forward, toward a future written in the same physics that made you. The night sky, with all its light and silence, is a mirror of what you are and what the universe will become. Perhaps, in the end, the cosmos isn't truly dying. Perhaps it's simply continuing its breath, softer, slower, until it becomes indistinguishable from peace. And in that peace, in that final, infinite quiet, the story doesn't vanish, it only changes form. The energy that once flared as galaxies and stars, that once thought and dreamed within you, will remain part of the same eternal unfolding. So as this long journey draws to a close, take a moment to breathe with it. The universe is still expanding, still alive in every atom, every pulse of light. Whether your eyes are open or already drifting towards sleep, remember, the cosmos continues. In you, in everything, in the gentle hush between seconds.